Hello there and welcome to Life Beyond Seen, where curiosity slows down a little, details matter, and science is explored in a calm, steady way that lets the mind wander without getting lost. Tonight's topic takes us far north, to a place most people will never visit, a place that looks simple on a map but turns out to be anything but simple once you try to study it closely. The North Pole often appears in textbooks as just the very top of the Earth, a white patch of floating ice surrounded by cold ocean, yet scientists who work in polar research will quietly admit that some parts of that region still resist careful, consistent study. Not because nobody cares, and not because the technology does not exist, but because the combination of environment, logistics, politics, and safety makes certain areas difficult enough that many research teams choose to focus elsewhere first. It sounds a bit surprising at first. After all, we have spacecraft orbiting Mars, robotic submarines exploring deep ocean trenches, and weather stations in deserts where summer heat melts electronics. Compared with all that, a frozen ocean might sound straightforward, but conditions near the northernmost parts of the planet create a mix of challenges that stack on top of one another. Travel windows are short, ice shifts without warning, equipment behaves differently than expected, communication links drop out. Even the basic act of standing safely on what looks like solid ground requires constant checking, because that ground may actually be a moving sheet of sea ice, only a few meters thick. Before going further, take a moment to notice where you are right now. Maybe you are listening at home, maybe travelling, maybe somewhere quiet after a long day. Where are you listening from tonight, and what time is it there? It is always interesting how a conversation about a remote place connects people sitting in completely different climates, different time zones, different routines. Someone might be hearing this while snow falls outside their window, someone else while a warm evening breeze comes through an open door. That contrast makes discussions about the far north feel a little more real. If you find this kind of calm exploration helpful, or simply enjoyable to listen to, a quick like or subscription helps the channel reach others who appreciate slower, thoughtful science discussions. It keeps this small space going, and it tells the platform that quiet curiosity still has a place online. No pressure, of course, just an open invitation. Now, when most people picture the North Pole, they imagine a fixed point covered in thick ice, perhaps with a research station planted firmly on top. The reality is more complicated. Unlike Antarctica, which is a continent with rock underneath the ice, the Arctic Ocean at the pole has no land beneath most of it. The ice there floats. That means research bases cannot simply be built once and left for decades. Ice camps drift, sometimes dozens of kilometers in a week, sometimes breaking apart entirely. Scientists often land aircraft on prepared ice runways, knowing those runways may need to be rebuilt after storms or shifts in pressure ridges. These moving conditions influence what research gets done. Long-term instruments need stable placement. Seismic sensors, atmospheric sampling towers, and deep drilling rigs work best when the ground stays put. At the pole, stability is temporary. Teams must constantly adapt. This leads to gaps in long-duration data sets, which is one reason certain areas remain less understood than many assume. Temperature is another obvious factor, but the specific ways extreme cold interferes with research are often underestimated. Batteries drain quickly, lubricants thicken, plastics become brittle enough to crack under minor stress. Even metal behaves differently when temperatures stay far below freezing for weeks. Cameras fail, cables stiffen, seals shrink. Researchers design specialized equipment, yet failures still occur often enough that redundancy becomes essential. Carrying duplicates increases weight, which increases fuel requirements, which raises costs and logistical complexity. Then there is darkness. For several months each year the sun does not rise at the pole. Continuous darkness affects both instruments and people. Solar-powered stations stop working unless backed by generators. Visual observation becomes difficult. Aircraft operations become riskier. Human circadian rhythms shift, sometimes causing sleep disruption and fatigue. teams train for this, but the effect never disappears completely. Communication infrastructure also behaves differently at high latitudes. Many satellites orbit closer to the equator, which means signals near the pole arrive at shallow angles or drop out entirely. Newer satellite constellations have improved coverage, but high-bandwidth, reliable connections remain harder to maintain than in mid-latitude regions. Data sometimes must be stored locally until a transmission window opens. That delay complicates real-time monitoring and remote troubleshooting. Weather variability adds another layer. Arctic storms can form quickly and move unpredictably across the polar basin. Visibility drops. Winds rearrange snow cover, hiding crevasses or opening new leads of water between ice floes. Helicopter flights cancel frequently. Ships navigating the marginal ice zone adjust routes constantly. Every delay increases operational cost, which influences how often institutions approve new expeditions. Cost is not a small detail. Polar research involves icebreakers, specialized aircraft, insulated habitats, survival training, and contingency planning for emergencies that may take days to resolve. Funding agencies balance these expenses against other scientific priorities. As a result, some regions receive regular study while others remain occasional targets, rather than continuous observation sites. Political boundaries, though less visible on ice than on land, also matter. Arctic nations maintain economic zones and research regulations. Permits must be secured. Environmental guidelines restrict certain activities to protect fragile ecosystems. These protections are important, but they add administrative steps that can delay projects by months or years. Wildlife presence is another practical consideration. Polar bears inhabit much of the Arctic Ocean's ice margin. Researchers train extensively in wildlife safety. Camps maintain watch rotations. Non-lethal deterrents are standard equipment. Encounters are rare, but serious enough that safety planning becomes a permanent part of fieldwork design. Interestingly, some of the least understood parts of the Arctic are not the coldest or darkest areas, but transitional zones where sea ice forms and melts seasonally. These regions change rapidly year to year. Instruments placed one season may end up in open water the next. Long-term monitoring becomes complicated because the baseline environment itself shifts. Climate change has intensified this variability. Thinner ice forms later and melts earlier. Routes once considered reliable become uncertain. New shipping paths open while others close unpredictably. For scientists, that means previous experience does not always predict future conditions. Planning now includes broader uncertainty margins. Historical exploration accounts add context. Early expeditions in the 19th and early 20th centuries often struggled simply to reach high latitudes. Navigation depended on celestial sightings and dead reckoning. Ice pressure crushed ships. Supplies ran low. Those accounts still inform modern risk assessments. While technology has advanced enormously, the fundamental environment remains challenging. Modern icebreakers and research vessels improve access, but even the most capable ships respect certain limits. Multi-year pressure ridges can rise several meters above the surface, with much thicker ice below. Progress slows, fuel consumption rises, mission timelines stretch. Captains make conservative decisions because mechanical failure far from support infrastructure carries significant risk. Aircraft operations follow similar caution. Runway construction on ice requires continuous monitoring. Temperature fluctuations change ice strength. Snow accumulation alters surface friction. Logistics teams survey repeatedly before allowing heavy cargo flights. Each check consumes time and personnel resources. Psychological factors also influence site selection. Extended isolation, confined living spaces, limited daylight, and environmental monotony affect mood and cognitive performance. Polar research programs include psychological screening and support systems, but agencies still consider team well-being when planning remote deployments. Some areas are simply too isolated for extended seasonal staffing with current support capacity. Data interpretation introduces another subtle challenge. Magnetic field behaviour near the pole differs from lower latitudes. Instruments sensitive to electromagnetic interference require calibration adjustments. Navigation systems dependent on magnetic compasses become unreliable. GPS works, but precision corrections are necessary for certain measurements. Sound propagation in cold polar air differs as well. Acoustic monitoring of ice movement, marine mammals, or atmospheric events requires tailored models. Standard assumptions used in temperate climates do not always hold. Researchers adapt methodologies, yet cross-comparison between datasets can be tricky. All these elements combine into a situation where avoidance is rarely absolute. Scientists are not forbidden from these areas. Rather, they weigh effort against expected data return. Sometimes the answer is to wait for better technology, more funding, or more favourable conditions. That quiet, strategic waiting can look like avoidance from the outside, and that brings the conversation gently toward the practical reality behind the idea that some northern polar zones remain lightly studded. It is not mystery in the dramatic sense, not hidden secrets under the ice, but a steady list of constraints that shape where people go, how long they stay, and what they measure once they arrive, which naturally leads into looking more closely at what those scientific blind spots actually are, and how researchers identify them while planning the next wave of Arctic exploration. When people look at a modern world map filled with satellite imagery, climate data dashboards, and real-time weather updates, it can feel as though every part of the planet has already been carefully measured and catalogued. The Arctic Ocean, especially the region surrounding the North Pole, often appears in those maps as a continuous white cap with occasional lines showing shipping routes or drifting research stations. From a distance, it gives the impression of completeness, as if the scientific picture is already filled in. Yet researchers working in polar science regularly point out that large portions of that region remain only partially understood. Not unknown in a dramatic sense, but lacking the kind of consistent long-term data that allows confident conclusions. Those gaps are what scientists sometimes call blind spots. One of the main reasons these blind spots persist comes down to the way scientific observation normally works. Reliable knowledge usually depends on repetition. Measurements taken once or twice give hints, but patterns emerge only when instruments collect data continuously across many seasons or years. In mid-latitude environments, maintaining those continuous observations is relatively straightforward. Weather stations stay fixed, ocean buoys anchor securely. Ground sensors operate year-round with occasional maintenance visits. Near the North Pole, that continuity becomes harder to maintain because the environment itself refuses to stay still. Sea ice motion is a good starting example. The Arctic Ocean's ice cover is not a static platform. It drifts under the influence of winds, currents, and temperature changes. A research station established on an ice floe in spring may be dozens or even hundreds of kilometers away by autumn. Instruments designed to monitor a specific geographic point suddenly measure conditions somewhere else. Scientists compensate by tracking drift carefully, but doing so complicates comparisons with previous data sets collected in slightly different locations. Over time, those subtle geographic differences create gaps in long-term regional understanding. Ice thickness measurement illustrates another aspect of the problem. Satellites estimate thickness indirectly using radar or laser altimetry, calculating how much ice protrudes above the water surface. That method works reasonably well, but it benefits from ground truth data, direct drilling measurements that confirm satellite estimates. Obtaining those ground measurements consistently across remote central Arctic zones requires repeated expeditions, which are expensive and weather-dependent. As a result, some regions have sparse calibration data, leaving uncertainty margins wider than researchers would prefer. Oceanographic sampling faces similar constraints. The Arctic Ocean influences global climate through heat exchange, fresh water storage and circulation patterns, yet continuous deep water measurements near the pole remain limited. Autonomous floats exist, but many were originally designed for open oceans. Sea ice cover interferes with their ability to surface and transmit data. Engineers have developed ice-capable floats, though deployment density is still lower than in temperate oceans. Each instrument lost under shifting ice represents not only equipment cost, but also lost months or years of potential observations. Atmospheric measurements also show uneven coverage. Polar meteorology affects global weather patterns through jet stream interactions and temperature gradients, but the number of permanent high-latitude stations remains relatively small. Temporary camps collect valuable seasonal data, yet gaps appear between campaigns. Satellites provide broad coverage, but they measure indirect indicators rather than the full vertical atmospheric profile that ground-based balloons and towers can deliver. Darkness during polar winter amplifies these challenges. Instruments dependent on solar power must switch to batteries or fuel generators, increasing maintenance needs. Human teams operate under stricter safety constraints. Aircraft flights become riskier due to limited visibility and rapidly changing weather. Some programs intentionally avoid winter deployments, which leaves seasonal blind spots in datasets that scientists later try to interpolate. Funding cycles add another layer. Scientific grants often operate on multi-year timelines with defined deliverables. Arctic fieldwork sometimes requires longer preparation and contingency buffers than those timelines comfortably allow. Delays caused by ice conditions, permit processing, or logistical bottlenecks can push projects beyond funding windows. Institutions therefore prioritize regions where data collection reliability is higher, unintentionally reinforcing uneven geographic coverage. There is also the issue of interdisciplinary coordination. The Arctic is studied by climatologists, oceanographers, geologists, ecologists, atmospheric chemists, and more. Each discipline designs campaigns based on its own priorities. Coordinating simultaneous measurements across multiple fields in a remote polar location requires substantial planning. When coordination succeeds, the resulting datasets are rich. When schedules misalign, valuable cross-disciplinary context can be missing. Environmental protection policies play an important role too. Arctic ecosystems are sensitive. Noise, emissions, physical disturbance, and potential contamination must be minimized. Certain regions receive restricted access status to protect wildlife habitats or indigenous subsistence areas. These protections are necessary, yet they limit where heavy research operations can occur. Scientists respect those limits, even when it means postponing specific measurements. Technological limits continue to evolve. Remote sensing improves steadily, but certain variables still require direct contact measurement. Chemical sampling of seawater, microbial ecology studies, and ice core drilling cannot be fully replaced by satellites. Until autonomous systems become more capable, human presence remains necessary for many observations, and that presence remains costly and logistically demanding. Navigation complexity near the pole contributes indirectly to blind spots as well. Traditional compass navigation becomes unreliable at high magnetic latitudes. Modern GPS mitigates this, yet precision positioning for some geophysical measurements requires additional correction systems. Establishing those systems in remote ice-covered waters takes effort that not every project can justify. Data transmission constraints influence project design. High-bandwidth satellite links in polar regions remain more limited than at lower latitudes. Large datasets sometimes must be stored locally until retrieval missions. That delay reduces opportunities for real-time analysis and adaptive sampling, where researchers adjust measurements based on early results. Without immediate feedback, some exploratory opportunities are missed. Human resource considerations matter too. Polar fieldwork demands specialized training in cold weather survival, equipment operation, and emergency response. The pool of experienced personnel is smaller than for more accessible environments. Scheduling conflicts, institutional commitments, and personal considerations all influence who can participate in a given expedition. That affects how often specific regions receive attention. Historical momentum also shapes research geography. Areas studied extensively in the past often continue receiving focus, because they provide long baseline records. Newer or more remote zones require initial investment without immediate comparative context. Funding agencies sometimes prefer extending existing datasets rather than starting entirely new ones, which is scientifically sensible but perpetuates uneven coverage. Climate variability introduces uncertainty into planning. Sea ice extent has shown significant year-to-year fluctuation. A route open one summer may close the next. Equipment caches placed for future use may become inaccessible. Flexibility helps, yet flexibility costs money, and budgets rarely stretch indefinitely. Safety considerations never disappear from planning discussions. Emergency evacuation options are limited far north. Medical support requires airlift capability. Weather windows for rescue flights can close suddenly. Institutions balance scientific value against acceptable risk thresholds, occasionally deciding that postponement is wiser than pressing forward. Acoustic monitoring of marine environments highlights another blind spot source. Sound travels differently under ice-covered seas. Ice ridges, temperature gradients, and salinity layers alter propagation paths. Installing long-term hydrophone arrays in moving ice fields requires careful anchoring strategies. Some arrays succeed, others are lost, leaving discontinuous acoustic records. Chemical tracer studies face sampling density challenges. Understanding pollutant transport, carbon cycling, and nutrient distribution requires widespread sample networks. Sparse station spacing near the pole reduces spatial resolution. Scientists model gaps statistically, but models always carry uncertainty. Biological studies encounter seasonal timing constraints. Certain Arctic species appear only during brief windows tied to ice melt, plankton blooms, or migration cycles. Missing that window can delay observations by an entire year. Weather disruptions during those windows compound the issue. International collaboration helps address many of these obstacles. Shared icebreaker missions, coordinated satellite programs, and multinational research initiatives expand coverage. Yet coordination requires diplomatic agreements, shared standards, and data-sharing frameworks that take time to establish. Progress continues, though slowly. Technological optimism remains strong. Autonomous drones, improved satellite constellations, long-endurance underwater vehicles, and better cold-resistant materials all promise increased coverage. Still, deployment at scale takes time. Prototypes prove concepts, then funding, manufacturing, and logistics determine how quickly those concepts spread. Even public perception plays a subtle role. Dramatic imagery of melting ice or polar wildlife attracts attention, but quieter foundational measurements receive less media focus. Funding priorities sometimes follow visibility, influencing which research proposals gain momentum. All of this creates a situation where the Arctic is neither unexplored nor fully understood. Instead, it contains gradients of knowledge. Coastal zones near established infrastructure are relatively well studied. Central drifting ice regions less so. Transitional seasonal ice edges present rapidly changing targets. Scientists acknowledge these gradients openly, using them to guide future research strategies. Understanding blind spots is itself productive. Mapping where data is sparse helps allocate resources more efficiently. It encourages methodological innovation. It fosters collaboration between disciplines and nations. Recognition of uncertainty often drives scientific progress rather than hindering it. As research capacity grows and technology improves, some of today's blind spots will narrow. Others may appear as environmental conditions change. Science rarely reaches a final map. It keeps refining, adjusting, and expanding. In the Arctic, that ongoing process continues quietly, shaped by practical realities more than dramatic mystery, and those realities connect directly to the physical challenges of the region itself, especially the geography, the ice, the darkness, and the isolation that influence every expedition heading toward the top of the planet. When scientists talk about the Arctic in practical terms, geography usually comes up before anything else. not the kind of geography that focuses on borders or place names, but the physical reality of a region that behaves very differently from most parts of the planet. The North Pole sits in the middle of the Arctic Ocean, not on solid land. That single detail shapes nearly every research decision. A floating surface changes how equipment is installed, how long people can stay, how transport works, and how reliable measurements remain over time. It also explains why some locations remain lightly studied even now, despite advances in technology. Sea ice is often described casually as a frozen cap, but in practice it resembles a slow, constantly shifting mosaic. Individual ice flows form, fracture, collide, stack into pressure ridges, thin during warmer periods, and drift under the influence of wind and currents. This movement is not gentle background motion. Floes can rotate, separate suddenly, or compress with enough force to deform thick ice. For a research team operating on the surface, stability is temporary. Structures must be designed for mobility or quick removal. Long-term fixed installations are rare because the platform itself rarely stays fixed. Thickness variation complicates matters further. Some areas contain multi-year ice several meters thick, while nearby sections may consist of recently formed ice thin enough to crack under modest load. Snow cover can disguise these differences. From a distance, the surface may look uniform, yet ground surveys often reveal uneven strength. That uncertainty influences where aircraft land, where drilling occurs, and where heavy instruments can safely operate. Logistics planning therefore starts with reconnaissance. Satellite imagery, radar surveys, and aerial observation help identify candidate sites. But conditions can change between observation and arrival. Teams often carry portable radar units to reassess ice thickness continuously. This constant verification consumes time and resources. It also limits how ambitious field deployments can be, because safety margins must remain conservative. Darkness introduces another dimension to geographic difficulty. For several months each year, the polar night removes direct sunlight entirely. Unlike typical winter darkness at lower latitudes, this period involves continuous night. Twilight may appear briefly depending on latitude, but full daylight does not return until late winter. Visual navigation becomes more complex. Ice surface features that would be obvious in sunlight require artificial lighting to detect. Shadows behave differently under low-angle illumination. Even experienced personnel adapt slowly each season. Instrument performance shifts under prolonged darkness as well. Solar-powered stations require alternative energy sources. Fuel generators become common, yet transporting fuel across drifting ice requires careful planning. Wind turbines sometimes supplement power, but wind conditions vary unpredictably. Battery technology has improved, though extreme cold still reduces capacity and lifespan. Engineers design insulated housings, yet maintenance intervals remain shorter than in milder environments. Human physiology reacts to sustained darkness in measurable ways. Sleep cycles shift, alertness patterns change, mood variations appear even among experienced polar researchers. Programs include psychological preparation, structured daily routines, and light therapy equipment to stabilize circadian rhythms. Despite those measures, productivity during polar night can differ from summer operations, affecting the amount and type of research scheduled during that period. Isolation extends beyond simple distance from populated areas. The Central Arctic lacks permanent settlements, infrastructure, and rapid emergency response capability. Transport depends primarily on icebreakers and specialized aircraft. Weather conditions frequently disrupt both. A storm system can delay flights for days. Sea ice movement can block ship access. These interruptions influence project timelines and sometimes force early termination of field campaigns. Communication infrastructure mirrors this isolation. Satellite coverage at high latitudes has improved, especially with newer constellations, but bandwidth limitations and signal interruptions still occur. Large data transfers may require scheduling during optimal satellite passes. Real-time remote troubleshooting becomes less reliable. Teams prepare for greater autonomy, carrying spare components and diagnostic tools because external support may not be immediately reachable. Mapping accuracy also deserves attention. Standard geographic coordinate systems converge near the pole, making directional orientation less intuitive. Longitude lines meet, reducing the usefulness of conventional east-west distinctions. Navigation software compensates mathematically, yet human interpretation requires adjustment. Survey teams train specifically for polar coordinate handling to avoid errors in instrument placement or route planning. Weather patterns interact strongly with geography. The Arctic atmosphere behaves differently due to temperature gradients between ice-covered ocean and surrounding continents. Fog formation can be rapid. Wind patterns shift as pressure systems move across the polar basin. Visibility conditions that appear stable in the morning can deteriorate quickly. This variability affects aircraft scheduling, icebreaker navigation, and outdoor research tasks. Ice leads, the open water channels that form between floes, present both opportunity and hazard, and scientists study heat exchange, gas transfer, and biological activity in these leads. At the same time, their unpredictable formation can isolate field camps or disrupt planned routes. A lead opening overnight may require rerouting travel paths or relocating equipment. Safety protocols include constant monitoring and contingency planning for such events. Temperature variability, while consistently cold overall, still fluctuates enough to affect surface conditions. Periods of relative warmth can soften snow cover, reduce ice strength, or increase meltwater pooling on the surface. Subsequent refreezing creates uneven terrain. Vehicles designed for polar travel must handle these mixed surfaces. Maintenance demands increase accordingly. Another geographic factor involves bathymetry, the underwater topography beneath the Arctic Ocean. Seafloor ridges, basins, and continental shelf extensions influence ocean circulation patterns. Mapping these features requires ice-capable research vessels equipped with sonar systems. Coverage remains incomplete in some central regions, because ship access is limited by ice conditions and seasonal windows. Sound propagation under ice differs from open ocean conditions. Ice cover reflects and refracts acoustic signals, affecting sonar mapping and marine life monitoring. Calibration requires localized measurements. Without those calibrations, interpreting acoustic data becomes less certain. This adds another layer to geographic complexity because surface conditions directly affect subsurface observations. Environmental protection considerations intersect with geography as well. Certain regions host sensitive wildlife habitats, seasonal migration corridors, or breeding grounds. Regulations limit disturbance levels, restrict access during specific periods, or require additional environmental impact assessments. Compliance is standard scientific practice, though it influences scheduling and site selection. Political geography overlays physical geography. The Arctic includes economic zones claimed by surrounding nations. Research expeditions often require permits from multiple authorities depending on planned routes. International collaboration helps, but administrative coordination adds time to preparation phases. These processes are routine yet contribute to uneven research distribution. Historical expedition routes continue to influence modern logistics. Established resupply paths, known safe anchorage zones, and previously used landing sites provide reference points. New regions without such historical data require more extensive preliminary surveys. Institutions sometimes prioritize familiar corridors for efficiency, which can leave adjacent areas less studied. Technological adaptation remains ongoing. Ice-strengthened hull designs, advanced navigation radar, and cold-resistant materials improve access. Autonomous surface vehicles and drones expand observation reach. Even so, deploying new technology in extreme geographic conditions involves testing cycles that slow widespread adoption. Reliability must be proven before instruments become standard tools. Biological sampling illustrates geographic constraints clearly. Plankton blooms, marine mammal presence, and fish distributions vary with ice edge position. Because the ice edge shifts seasonally, consistent sampling locations are difficult to maintain. Scientists track moving ecological boundaries rather than fixed coordinates, complicating long-term comparisons. Permafrost research near Arctic coastlines connects indirectly to central polar studies. Changes in coastal permafrost affect sediment transport and freshwater input into the Arctic Ocean. Monitoring those inputs requires integrated coastal and offshore observations. Geographic separation between disciplines sometimes delays comprehensive data sets. Emergency response planning reflects geographic reality in practical ways. Medical evacuation from central Arctic locations may involve multiple transport stages, helicopter to icebreaker, then aircraft to mainland facilities. Weather delays can extend response times significantly. Research teams include trained medical personnel and equipment to manage emergencies until evacuation becomes possible. Fuel storage and waste management require careful geographic consideration. Transporting supplies across drifting ice necessitates secure storage solutions that account for movement, temperature variation, and environmental protection standards. Waste removal follows strict guidelines to avoid contamination. These logistical tasks consume significant expedition capacity. Even simple daily activities reflect geographic constraints. Constructing temporary shelters, maintaining safe walking paths across uneven ice, managing snow accumulation around equipment, and monitoring wildlife all become routine responsibilities. Scientific measurement shares time with operational maintenance in ways uncommon in more stable environments. Educational outreach sometimes shapes expedition planning too. Public interest in Arctic science supports funding, but communication from remote geographic locations is technically challenging. Teams schedule transmissions carefully, balancing outreach with bandwidth limitations and operational priorities. Despite all these factors, scientific interest in the Arctic remains strong because the region plays a critical role in global climate systems, ocean circulation, and atmospheric dynamics. Understanding it requires persistence. Researchers accept geographic difficulty as part of the work, adjusting methods rather than abandoning objectives. Technological progress continues to reduce some barriers. Improved satellite imaging offers higher resolution ice monitoring. More efficient cold weather batteries extend instrument life. Autonomous vehicles operate under ice for longer periods. Each improvement narrows certain gaps, though none eliminate the underlying geographic challenges entirely. Experience accumulates gradually. Field manuals expand. Best practices evolve. Collaboration networks strengthen. Knowledge gained from one expedition informs the next. This incremental approach mirrors the environment itself, steady, sometimes slow, but consistently moving forward. All of these geographic realities explain why certain northern polar areas still receive intermittent rather than continuous scientific attention. The combination of floating ice, extended darkness, and profound isolation shapes every decision researchers make. Recognizing those constraints does not discourage exploration. Instead, it helps refine how future work is planned, especially when considering how extreme weather patterns interact with that geography, and further influence where scientists can realistically operate over long periods. Weather in the Arctic is often described simply as cold, but that description leaves out the details that actually shape scientific work there. Cold is only one element in a broader system that includes rapidly changing wind patterns, shifting pressure systems, seasonal temperature swings, visibility fluctuations, and interactions between ocean, ice, and atmosphere. These factors combine in ways that make long-term research planning far more complicated than it would be in a stable climate zone. Scientists do operate successfully in the Arctic, yet the environment frequently forces adjustments, pauses, or complete redesigns of research projects intended to run continuously over months or years. Wind is one of the first factors researchers account for when planning fieldwork. Arctic winds are not constant breezes. They often arrive in bursts associated with passing low-pressure systems. These winds move sea ice, sometimes gradually, sometimes abruptly. A research station established on an apparently stable flow can drift significantly over a short period if strong winds persist. That drift complicates long-term measurement because instruments begin sampling different water masses, atmospheric conditions, or ecological zones than originally intended. Data remains useful, but interpretation requires additional correction and context. Wind also reshapes snow cover. Snowdrifts accumulate unevenly, burying instruments or exposing ice surfaces unexpectedly. A meteorological tower that stood clear one week may be partially buried the next. Teams must conduct routine excavation and repositioning. This ongoing maintenance takes time away from primary scientific tasks. It also increases wear on equipment designed to remain stationary. Storm systems in the Arctic can develop quickly, especially during seasonal transitions. These storms may bring strong winds, heavy snowfall, and rapid temperature shifts. Aircraft operations usually halt during such conditions. Helicopter flights transporting personnel or equipment become unsafe due to low visibility and turbulence. Ships navigating through pack ice reduce speed or change course. A planned resupply mission may be delayed days or weeks, forcing research teams to stretch existing supplies and adjust schedules. Temperature fluctuations deserve closer attention as well. Although the Arctic is consistently cold compared with the temperate regions, short-term variations still matter. A period of relatively warmer air can soften surface snow, weaken ice integrity, or create meltwater pools. When temperatures drop again, those pools refreeze unevenly, forming ridges or slick surfaces that complicate travel. Instruments calibrated for stable conditions sometimes require recalibration after such cycles. Cold air interacting with relatively warmer ocean water produces fog, which can persist for extended periods. Fog reduces visibility dramatically. Visual navigation becomes difficult. Optical sensors collect less reliable data. Aircraft and drone operations frequently pause because pilots rely heavily on visual reference points in a landscape already lacking distinct landmarks. This fog-related downtime reduces the amount of continuous observational data scientists can collect. Blizzards present another obstacle. Snowfall combined with strong wind produces whiteout conditions where horizon lines disappear. Researchers describe situations where ground and sky blend visually, making depth perception unreliable. Outdoor work becomes hazardous. Teams restrict movement to essential tasks only. Instruments exposed during a blizzard may accumulate ice or snow layers that alter readings until maintenance crews can safely access them again. Sea ice pressure events are indirectly weather-driven but significant. Sustained winds push ice floes together, creating pressure ridges. These ridges can rise several meters above the surface while extending much deeper below. Research camps located near such compression zones must sometimes relocate quickly. Moving an entire camp involves dismantling shelters, securing instruments, transporting fuel, and re-establishing safety perimeters. Each relocation interrupts data continuity. Ocean swell occasionally penetrates into the ice pack from distant storms. Even when local weather seems calm, swell transmitted through open water regions can flex ice sheets. This flexing stresses structures placed on the ice. Instruments anchored in drilled holes may loosen. Runways carved into ice require resurfacing. These indirect weather influences are less visible, but still significant. Electrical storms are rare but not non-existent. Lightning risk is low compared with lower latitudes, yet atmospheric electrical activity can interfere with sensitive instruments. Static buildup affects communication equipment. Calibration checks become necessary after such events to ensure data integrity. Seasonal transition periods are particularly unpredictable. Spring melt introduces melt ponds, thinner ice sections, and increased wildlife activity. Autumn freeze-up creates unstable new ice that appears solid but may not support heavy equipment. Planning long-term research across these transitions requires flexible scheduling and contingency budgeting. Humidity behaves differently in cold environments. Extremely cold air holds little moisture, but temperature fluctuations can cause frost buildup on exposed equipment. Optical sensors, antennas, and ventilation systems accumulate ice crystals. Removing these safely requires regular inspection. Neglecting frost buildup can degrade instrument accuracy over time. Solar radiation variability also plays a role. During summer months, continuous daylight affects temperature gradients differently than typical day-night cycles. Snow surface reflectivity, known as albedo, influences local warming patterns. Researchers studying energy balance must account for these variations carefully. Continuous sunlight simplifies some observations but complicates others. The polar vortex, a large-scale atmospheric circulation pattern, occasionally weakens or shifts position. When that happens, colder air masses move differently, affecting Arctic weather unpredictably. These broader atmospheric changes influence local conditions, sometimes bringing unexpected warmth or intensified cold snaps. Long-term research designs incorporate statistical expectations, yet real-world deviations still cause operational adjustments. Climate change has introduced additional variability. Sea ice extent has declined overall, but the pattern is not uniform year to year. Some seasons see temporary rebounds, others sharp reductions. Thinner ice responds more quickly to wind and temperature changes, amplifying mobility issues. Researchers must update risk assessments continuously rather than relying solely on historical averages. Marine conditions beneath the ice respond to weather above. Strong winds enhance mixing in open water areas, altering salinity and temperature profiles. These changes affect biological productivity and chemical exchange rates. Without continuous measurement, scientists rely on intermittent sampling, leaving temporal gaps in data sets. Storm-driven precipitation can affect atmospheric chemistry measurements. Snowfall scavenges airborne particles, temporarily reducing concentrations. Instruments must distinguish between true environmental change and weather-related short-term variation. This distinction requires contextual meteorological data, which may itself be incomplete during severe conditions. Resupply logistics depend heavily on weather windows. Icebreakers require navigable leads. Aircraft require acceptable visibility and wind limits. Missed resupply opportunities increase operational risk. Teams sometimes scale back research scope to conserve fuel or spare parts until the next transport opportunity arrives. Emergency planning incorporates worst-case weather scenarios. Evacuation may be impossible for extended periods. Medical supplies, redundant power systems, and communication backups become essential. This preparation adds weight and cost, influencing how much scientific equipment can be transported initially. Weather impacts psychological resilience too. Continuous storms, limited outdoor mobility, and prolonged darkness affect morale. Team cohesion strategies, structured schedules, and communication with support networks help maintain well-being. Institutions consider these human factors when deciding whether to extend or shorten deployments. Instrument design evolves in response to these challenges. Heated enclosures, reinforced mounting systems, and weather-resistant materials improve reliability. Still, no design eliminates all risk. Engineers test prototypes extensively before Arctic deployment, but real conditions often reveal unforeseen issues. Remote sensing offers partial solutions. Satellites observe large areas regardless of ground weather, though cloud cover can obscure optical imagery. Radar systems penetrate clouds but interpret surface characteristics differently. Combining satellite and ground data provides the most complete picture, yet ground validation remains essential. Data continuity is often the central concern. Long-term climate studies require consistent measurement intervals. Weather-related interruptions introduce gaps that complicate trend analysis. Statistical methods fill some gaps, but direct observation remains preferable whenever feasible. Collaborative research networks help distribute risk, Multiple stations across the Arctic share data, so a disruption at one location does not halt entire projects. International partnerships strengthen this redundancy. Coordinated observation campaigns improve coverage despite local weather obstacles. Training emphasizes adaptability. Polar researchers learn to modify plans quickly, prioritize safety, and maintain equipment under challenging conditions. Experience accumulates gradually. Veteran field scientists pass practical knowledge to newer team members, improving overall resilience. Insurance and liability considerations influence project approval as well. Severe weather increases operational risk, which affects institutional policies. Risk mitigation strategies must be clearly documented before expeditions receive funding and authorization. Public interest in Arctic weather often focuses on dramatic imagery, but day-to-day operational impacts are more subtle. Minor delays, recalibrations, and maintenance tasks rarely make headlines, yet they shape the pace of scientific progress significantly. Despite these obstacles, researchers continue returning because Arctic weather processes influence global systems. Understanding those processes requires persistence, even when conditions interrupt ideal study schedules. Each expedition contributes incremental knowledge. Technology development continues addressing specific weather-related limitations. Improved forecasting models enhance planning accuracy. Stronger materials extend instrument lifespan. Autonomous systems operate during periods unsafe for human presence. Progress remains steady, even if gradual. Recognizing the influence of extreme weather helps explain why certain long-term Arctic research projects develop slowly. Interruptions are expected rather than exceptional. Scientists design studies with flexibility built in, accepting that environmental realities dictate pacing. These weather constraints connect directly with other practical challenges, including navigation complexity, magnetic irregularities, and technical limitations that appear more prominently as researchers push farther toward the pole, where conditions amplify subtle effects that might go unnoticed elsewhere. If you look at a standard world map, directions appear simple. North is up, south is down, east and west sit comfortably to either side. Most of daily navigation assumes those directions behave consistently everywhere. In much of the world, that assumption works well enough that people rarely question it. Near the North Pole, however, direction itself becomes a more complicated concept. Magnetic behavior shifts, navigation systems require adjustment, and the simple act of knowing which way you are facing demands more careful attention than most people ever need to consider. For scientists working in that region, these factors are not abstract curiosities. They influence safety planning, instrument placement, transport logistics, and the reliability of long-term research. The Earth's magnetic field is not perfectly aligned with its geographic axis. The geographic North Pole marks the planet's rotational axis, the point around which Earth spins. The magnetic North Pole, by contrast, represents a location where the magnetic field points vertically downward. That magnetic pole moves gradually over time due to fluid motion in Earth's outer core. Over decades, it has shifted hundreds of kilometers. This ongoing drift means that navigation references based on older magnetic data must be updated regularly, especially at high latitudes where small positional changes produce larger directional differences. Traditional magnetic compasses behave differently as one approaches the pole. At mid-latitudes, the magnetic field lines intersect the surface at moderate angles, allowing compass needles to pivot horizontally with relative stability. Near the pole, those field lines become steep. The needle begins to tilt downward rather than simply pointing north. Specialized compasses compensate mechanically, but even those instruments lose accuracy very close to the pole. Scientists planning over ice travel rarely rely on magnetic compasses alone. They treat them as supplementary tools rather than primary navigation sources. Global positioning system technology helps overcome many of these issues, yet it introduces its own complexities. GPS satellites orbit Earth in patterns optimized for global coverage, but signal geometry near the poles differs from lower latitudes. Signals arrive at shallower angles relative to the horizon. Multipath reflections off ice surfaces sometimes interfere with reception. Precision positioning therefore requires correction algorithms and occasionally additional satellite constellations to maintain reliability. Most research expeditions carry redundant navigation systems to reduce risk. Surveying accuracy becomes particularly important for scientific measurements. When researchers install atmospheric sensors, seismic monitors, or oceanographic sampling equipment, they must know exact coordinates to compare results over time. Ice drift already introduces movement. Navigation uncertainty adds another layer. Teams conduct repeated position checks using high-precision GPS receivers capable of differential correction. These receivers improve accuracy to centimetre scale, though they require stable satellite communication links and careful calibration. Magnetic anomalies themselves arise from several sources. Variations in crustal composition beneath the Arctic Ocean create localized magnetic distortions. Although the ocean floor remains largely hidden beneath ice, geophysical surveys indicate irregularities that affect compass readings subtly. These anomalies may not matter for casual navigation, but scientific instruments sensitive to electromagnetic interference require compensation. Magnetometers used to study Earth's field must distinguish between global field behavior and local geological influences. Atmospheric conditions can influence magnetic measurements too. Solar activity periodically disturbs Earth's magnetosphere, producing geomagnetic storms. At high latitudes, these storms generate auroras, but also cause fluctuations in magnetic field intensity. Instruments record temporary deviations. Communication systems occasionally experience interference. Scientists monitor solar weather forecasts alongside terrestrial weather forecasts to anticipate such events. Aircraft navigation systems incorporate magnetic references as well as inertial and satellite-based data. Near the pole, flight crews rely more heavily on inertial navigation and GPS. Autopilot algorithms account for convergence of longitude lines, which reduces the usefulness of conventional heading definitions. Aviation authorities publish special procedures for polar routes. These procedures address fuel planning, communication contingencies, and navigation adjustments unique to high latitudes. Marine navigation encounters related challenges. Ships traditionally used magnetic compasses alongside celestial navigation. Modern vessels integrate satellite navigation extensively, yet backup compass systems remain important. Icebreaker captains operating in the Central Arctic combine multiple data sources: GPS, radar imaging of ice features, sonar bathymetry, and visual observation when conditions allow. Navigation planning includes allowances for drift, magnetic variation, and potential signal loss. Scientific instruments designed to measure Earth's magnetic field face a paradox in polar regions. These areas provide valuable data about global magnetic dynamics, yet local variability complicates interpretation. Researchers deploy arrays of magnetometers spaced across large areas to average out localized distortions. Maintaining those arrays on moving ice platforms presents logistical challenges already discussed earlier. Data analysis therefore includes correction factors accounting for both geographic movement and field fluctuation. Directional drilling projects, though less common in central Arctic waters than in continental shelf areas, illustrate another navigation concern. Drilling equipment often relies on magnetic orientation tools. Near the pole, alternative orientation methods using gyroscopes or inertial systems become necessary. These systems add cost and complexity, but improve reliability where magnetic references weaken. Timekeeping intersects with navigation as well. Precise timing underpins GPS calculations. Atomic clocks aboard satellites maintain synchronization, yet ground receivers must also keep accurate time. Extreme cold can affect oscillator stability in portable equipment. Engineers design temperature-compensated timing modules, though field calibration remains important. Without precise timing, positional accuracy degrades. Human perception of direction can also be affected. In environments lacking familiar landmarks, individuals rely more heavily on instruments. Continuous daylight in summer and continuous darkness in winter remove visual cues like sunrise or sunset direction. Researchers receive orientation training to reduce disorientation risk. Camps often establish fixed visual markers to help maintain spatial awareness. Historical exploration accounts reveal how challenging navigation once was in these regions. Early expeditions relied on sextants, chronometers, and magnetic compasses with limited understanding of polar variation. Navigators sometimes recorded inconsistent bearings, complicating route reconstruction later. Modern technology has reduced uncertainty significantly, yet the underlying magnetic complexity remains. Geophysical research benefits from studying these anomalies. Changes in magnetic pole position provide clues about processes deep within Earth's core. Polar observatories contribute essential long-term data sets. Maintaining those observatories requires stable infrastructure in an unstable environment, reinforcing the interconnected challenges scientists face. Communication systems sometimes depend on high-frequency radio propagation, which interacts with the ionosphere. Polar ionospheric conditions differ from mid-latitudes, especially during geomagnetic disturbances. Signal quality fluctuates. Backup communication channels remain standard practice. Satellite phones, radio systems, and data relays provide layered redundancy. Survey aircraft mapping ice thickness or seabed topography must account for magnetic interference affecting onboard sensors. Calibration flights over known reference areas help maintain data accuracy. Such calibration opportunities are less frequent in remote polar regions, adding uncertainty margins. Autonomous vehicles operating under ice, including underwater drones, use inertial navigation systems because GPS signals do not penetrate water. Magnetic interference near the pole can affect onboard compasses, so designers combine multiple sensors, gyroscopes, accelerometers, Doppler velocity logs. Data fusion algorithms integrate these inputs to estimate position. Periodic resurfacing allows GPS correction when conditions permit. Cartographic representation near the pole requires projection adjustments. Standard map projections distort distances and angles significantly at high latitudes. Specialized polar projections reduce distortion, but still require careful interpretation. Scientists comparing data sets across projections must ensure coordinate transformations remain consistent. Educational training for polar researchers increasingly includes navigation science. Understanding magnetic variation, GPS correction methods, and coordinate system differences helps prevent operational errors. Simulation exercises prepare teams for signal loss scenarios. Emergency response navigation deserves special mention. Search and rescue operations rely on accurate positioning. Weather, magnetic anomalies, and drifting ice complicate these missions. Coordinated international protocols exist, but response times can be longer than in populated regions. Preventive navigation accuracy therefore becomes even more critical. Satellite development trends offer improvement prospects. Polar orbiting satellites provide better coverage than equatorial constellations. Increasing their number enhances reliability. Data latency decreases. Scientists anticipate gradual reduction in communication and navigation gaps as these systems expand. Magnetic field research itself continues advancing. Satellite missions dedicated to geomagnetic observation refine global models. Updated models feed into navigation software, improving accuracy for both civilian and scientific users. Continuous monitoring remains necessary because the magnetic field evolves constantly. Even recreational polar travel reflects these realities. Expedition guides use multiple navigation systems and maintain contingency protocols similar to scientific teams. Safety considerations extend beyond research contexts. All of these navigation complexities influence where scientists choose to work and how they design long-term studies. Regions with higher navigation uncertainty may receive shorter exploratory visits before sustained monitoring begins. Incremental approach reduces risk while building operational familiarity. Understanding magnetic anomalies does not discourage Arctic research. Instead, it shapes methodology. Scientists design instruments and protocols that accommodate variability rather than assuming uniform conditions. This adaptive approach mirrors broader polar research strategies. As exploration technology advances, some navigation challenges will continue to diminish. Others, rooted in Earth's fundamental magnetic structure, will persist. Researchers accept that certain complexities are permanent features of the environment. These navigation considerations connect closely with another practical issue already hinted at earlier: the stability of the ice surface itself. Even with accurate positioning, maintaining equipment on drifting, fracturing ice platforms introduces its own set of constraints, which naturally leads toward examining how unstable ice sheets influence research continuity in the far north. One of the most practical realities scientists face in the far north is that the surface they often work on is not land at all, but floating sea ice. At first glance, that ice can look solid and dependable, especially when it stretches to the horizon without visible breaks. In reality, it behaves more like a slowly shifting platform than a fixed foundation. This constant movement influences how research stations are built, how instruments are installed, how data is interpreted, and ultimately why some areas receive only intermittent scientific attention rather than continuous monitoring. Sea ice forms when ocean water freezes, but it does not form as one uniform sheet. Individual floes develop separately, then drift together under wind and current influence. Some freeze into larger masses, others collide and fracture repeatedly. Thickness varies widely even within short distances. Multi-year ice that has survived several summers can become several meters thick and relatively strong, while newly formed seasonal ice may measure less than a meter. Snow accumulation on top complicates visual assessment, masking thinner areas and sometimes adding weight that stresses the ice from above. When research teams establish temporary camps near the pole, they start by surveying ice thickness carefully. Ground-penetrating radar, drilling cores, and satellite imagery all contribute to site selection. Even after choosing a location, continuous monitoring remains necessary. A stable flow today may weaken after a storm, temperature shift, or internal stress buildup. Instruments anchored securely one week may require repositioning the next, simply because the underlying ice conditions have changed. Movement is constant even when it appears slow. Winds push floes across the Arctic Ocean, sometimes only a few kilometers per day, sometimes much faster. Ocean currents add another directional influence. Over months, entire research camps can drift hundreds of kilometers from their original deployment point. Scientists track that drift precisely because location matters for interpreting measurements. Atmospheric data, ocean salinity readings, and ecological observations all depend on geographic context. The drifting nature of ice creates both opportunities and complications. On one hand, a drifting station samples a range of conditions naturally as it moves, providing a broader data set than a fixed station might. On the other hand, consistency suffers. Comparing measurements from slightly different environments requires careful correction. Long-term trend analysis becomes more complex because the observation point itself is not constant. Pressure ridges form another major concern. When two ice flows collide, neither usually slides smoothly past the other. Instead, they compress, forcing ice upward into jagged ridges and downward into thick underwater keels. These ridges can rise several meters above the surface while extending much deeper below. They create uneven terrain that complicates vehicle travel, aircraft landings, and equipment placement. Researchers often must level small areas artificially to construct safe working surfaces. Cracking events can occur with little warning. Temperature fluctuations cause expansion and contraction. Wind stress accumulates until fractures open suddenly. A camp positioned safely on one flow can find itself separated by open water from supply routes within hours. Teams prepare contingency plans, including portable bridges, inflatable boats, and rapid relocation procedures. Safety drills are routine because response time matters. Aircraft operations illustrate how ice instability influences logistics. Cargo planes delivering supplies land on runways carved directly into ice. Engineers measure thickness repeatedly, monitor temperature changes, and inspect for hidden cracks. After heavy snow or wind events, runways require resurfacing. If ice integrity declines, flights suspend until a new landing area is prepared. These interruptions affect resupply schedules and sometimes limit the duration of research campaigns. Fuel storage presents additional challenges. Generators, heating systems, and vehicles require reliable fuel supplies. Storing fuel safely on moving ice requires insulated containers, spill prevention measures, and contingency plans in case of flow breakup. Environmental protection standards are strict because contamination in polar ecosystems has long recovery times. Instrument anchoring techniques vary depending on research goals. Atmospheric sensors may mount on towers secured with ice screws and weighted bases. Oceanographic instruments sometimes deploy through drilled holes, suspended below the ice on cables. Seismic sensors rest directly on the ice surface. Each method assumes a degree of stability that must be reassessed frequently. Recalibration after repositioning ensures data continuity. Autonomous platforms offer partial solutions. Drifting buoys equipped with sensors transmit data via satellite while following natural ice motion. These buoys extend observational reach without requiring permanent human presence. However, they remain vulnerable to crushing, submersion, or signal loss. Deployment density must remain high enough that losing some units does not compromise entire data sets. Under-ice autonomous vehicles add another layer of complexity. Submersible drones gather oceanographic data beneath ice where ships cannot easily operate. Navigation relies on inertial systems because GPS signals do not penetrate water. Ice movement above complicates resurfacing for communication or recovery. Engineers design sophisticated tracking protocols, though some vehicles are inevitably lost over time. Thermal processes influence stability continuously. Even during winter, heat exchange occurs between ocean and atmosphere. Thin ice grows thicker in cold conditions but can thin from below if warmer currents pass underneath. Surface snow acts as insulation, sometimes slowing further freezing. Predicting these processes accurately requires detailed modelling and constant measurement. Seasonal melt cycles intensify instability. As temperatures rise, melt ponds form on the ice surface. These pools absorb more solar energy than surrounding snow, accelerating local melting. Water draining through cracks weakens structural integrity. Researchers adjust travel routes frequently during melt season to avoid unexpectedly thin areas. Mechanical stresses accumulate invisibly within ice. Like any material, ice deforms under pressure. Over time, stress lines develop. When thresholds exceed, sudden fracture occurs. Acoustic monitoring systems sometimes detect precursors to large cracking events, though prediction remains imperfect. Continuous vigilance remains essential. Environmental considerations extend beyond safety. Wildlife interacts with ice surfaces. Polar bears use ice for hunting and travel. Seals maintain breathing holes. Disturbing these patterns carries ecological consequences. Research teams follow guidelines to minimize disruption, which sometimes limits where camps can be established. Human living conditions reflect these environmental realities. Temporary shelters must withstand shifting surfaces, strong winds, and extreme cold. Foundations use flexible anchoring systems. Interior heating systems operate continuously. Maintenance demands remain constant because small structural issues can escalate quickly in harsh conditions. Psychological adaptation also plays a role. Knowing that the ground itself moves subtly beneath daily activities requires mental adjustment. Experienced polar researchers describe developing an awareness of ice sounds, vibrations, and visual cues indicating change. Training programs prepare newcomers for these experiences to reduce anxiety and improve response readiness. Communication infrastructure on moving ice requires portability. Satellite antennas mount on adjustable platforms. Cables route through protective conduits, allowing repositioning. Power generation units include redundancy in case one system fails during relocation. Engineers design modular camp layouts for efficient dismantling. Scientific data interpretation always accounts for platform motion. GPS tracking provides precise drift records. Researchers incorporate that positional data into analysis pipelines automatically. Without such corrections, datasets might suggest environmental change where only geographic movement occurred. Ocean circulation studies benefit from drifting stations in some cases. Following ice movement provides insight into current patterns. Scientists combine drift data with temperature and salinity measurements to improve circulation models. This synergy turns a logistical challenge into a scientific advantage. Long-term observatories sometimes anchor to thick multi-year ice deliberately chosen for relative stability. Even these sites require contingency planning, because climate trends indicate decreasing prevalence of thick perennial ice. Researchers monitor thickness trends continuously to anticipate future site viability. Ship-based research complements ice camps. Icebreakers provide mobile platforms capable of navigating through pack ice. Their presence reduces reliance on fixed camps but introduces fuel costs, crew requirements, and limited seasonal access. Ships often support shorter intensive campaigns rather than multi-year monitoring. Remote sensing technology has improved ability to track ice dynamics from space. Synthetic aperture radar satellites penetrate cloud cover and darkness, mapping ice motion and deformation. Scientists integrate these data with on-site observations for comprehensive understanding. Still, satellite resolution cannot replace all direct measurements. International collaboration has expanded significantly in recent decades. Shared drifting observatories, multinational icebreaker missions, and coordinated buoy networks distribute risk and cost. Cooperation allows broader coverage than any single nation could maintain independently. Historical context highlights progress. Early polar expeditions relied on ships intentionally frozen into ice to drift across the Arctic. Those missions provided valuable data but carried high risk. Modern technology improves safety considerably, though fundamental ice dynamics remain unchanged. Economic considerations influence platform choice. Establishing and maintaining a drifting camp requires substantial funding. Institutions evaluate expected scientific return carefully before committing resources. This evaluation sometimes favors regions with existing infrastructure, leaving more remote areas less studied. Environmental change continues altering the picture. Thinner ice increases mobility but reduces structural reliability. Scientists adapt methodologies continuously. Flexible platforms, autonomous systems, and hybrid ship ice operations reflect this adaptation. Educational outreach increasingly highlights these operational realities. Public understanding of Arctic research often focuses on climate data outcomes rather than logistical challenges. Greater awareness supports informed funding decisions and realistic expectations about research pace. Training programs for polar engineers and scientists emphasize multidisciplinary skills. Field personnel learn navigation, mechanical maintenance, environmental monitoring, and emergency response alongside scientific techniques. This versatility improves resilience on unstable platforms. Data management strategies account for possible loss. Instruments store local backups. Transmission redundancy ensures partial datasets survive even if equipment fails. Cloud storage integration has improved reliability, though bandwidth constraints persist. Safety culture remains central. Regular drills, conservative decision-making, and clear communication protocols reduce incident risk. Teams treat environmental unpredictability as routine rather than exceptional. Technological innovation continues steadily. Improved ice thickness sensors, stronger lightweight materials, and more efficient power systems enhance operational capability. Each advancement expands potential research duration slightly. Despite these improvements, the fundamental reality remains unchanged. Sea ice moves, cracks, thickens, thins, and responds dynamically to atmospheric and oceanic forces. Scientific work adapts to that motion rather than attempting to eliminate it. Researchers accept that some data gaps are inevitable. Understanding unstable ice platforms clarifies why continuous long-term observation near the pole develops gradually. The environment dictates pacing. Incremental progress accumulates through repeated expeditions, technological refinement, and international cooperation. This dynamic platform challenge also connects with broader issues already touched upon earlier, including restricted access zones shaped by political considerations, environmental protection policies, and historical claims, all of which influence where scientists can realistically operate even when technical capability exists. As research activity expands in the far north, another practical factor quietly shapes where scientists can work and how often they return to certain locations. It is not always ice thickness, storms, or darkness that limit access. Sometimes the constraints come from human decisions made for security, political, or regulatory reasons. Parts of the Arctic fall under national jurisdiction, and those jurisdictions occasionally include restricted zones connected to military operations, early warning systems, submarine navigation routes, or sensitive infrastructure. These areas are not secret in the dramatic sense often imagined in popular culture, but they do involve controlled access that can slow or redirect scientific work. The Arctic borders several nations including Canada, Russia, the United States, Norway and Denmark through Greenland. Each country maintains sovereignty over specific territorial waters and exclusive economic zones. Within those boundaries, governments may designate certain regions for defense-related monitoring. Radar installations, acoustic detection systems, airfields, and communication relay stations exist in some high-latitude areas because the polar region provides strategic transit routes between continents. Aircraft flying long-distance routes often pass over polar airspace, and naval vessels, including submarines, operate beneath Arctic ice. These realities naturally lead to security considerations. When an area carries defense significance, research access typically requires permits beyond standard environmental approvals. Scientists must submit project descriptions, equipment lists, personnel details, and intended travel routes well in advance. Approval timelines can stretch months or longer. Sometimes approval arrives with restrictions on instrument placement, data sharing, or operational timing. These conditions do not prevent research entirely, but they can make certain locations less attractive compared with sites where administrative processes move faster. Communication infrastructure sometimes overlaps with restricted zones. High-frequency radio arrays, satellite tracking stations, and radar facilities often operate in remote northern regions precisely because interference levels are low there. Scientific equipment emitting radio signals must avoid frequencies reserved for defense systems. Coordinating those frequencies requires technical consultation. This coordination ensures safety and prevents interference, yet it adds another layer of planning. Submarine navigation is one of the less visible influences on Arctic access policies. Beneath sea ice, naval vessels rely on acoustic mapping and inertial navigation. Some areas host monitoring arrays designed to track underwater movement. Exact locations are rarely public for security reasons. Research ships conducting acoustic surveys or deploying underwater vehicles sometimes adjust routes to avoid potential interference with those systems. These adjustments do not necessarily eliminate study opportunities, but they may alter data collection plans. Airspace restrictions occasionally affect atmospheric research as well. Polar atmospheric studies often involve research aircraft flying sampling missions at various altitudes. Military training flights or surveillance operations may temporarily restrict certain air corridors. Civil aviation authorities coordinate these schedules, though short-notice changes sometimes occur due to operational requirements. Scientists adapt by adjusting flight paths or rescheduling missions when necessary. environmental protection laws intersect with security considerations too. Some regions serve dual roles as wildlife conservation zones and limited access defence areas. For example, coastal Arctic locations may host both sensitive bird nesting grounds and radar installations. In such cases, research proposals undergo review from multiple agencies, including environmental regulators and defence authorities. Approval processes become more complex, but the goal remains balancing ecological preservation, national security and scientific advancement. Data sharing policies occasionally reflect these sensitivities. Measurements involving seafloor mapping, acoustic signatures, or detailed geographic surveys may require review before publication. The concern is not usually scientific content itself, but the potential for unintended disclosure of navigation-relevant information. Researchers remain free to publish most findings, though certain technical details may require generalization or delayed release. Historical context helps explain how these arrangements developed. During the mid-20th century, the Arctic gained strategic importance because of its position between major geopolitical powers. Early warning radar lines, submarine patrol routes, and experimental communication stations appeared in northern territories. Although geopolitical tensions have shifted over time, some infrastructure remains operational. Modern defence priorities emphasise monitoring rather than confrontation. Yet infrastructure continuity influences land and sea use patterns. International agreements attempt to maintain balance. The Arctic Council, for example, promotes scientific cooperation among Arctic nations. Military topics remain outside its formal mandate, but diplomatic engagement encourages transparency where possible. Joint scientific expeditions sometimes include participants from multiple countries, which can ease access issues through shared authorization frameworks. Scientific organizations generally approach restricted zones pragmatically. If access proves difficult, alternative sites with similar environmental characteristics may serve as substitutes. While this strategy helps maintain research momentum, it occasionally leaves specific microregions less studied, simply because administrative barriers outweigh expected data benefits. Satellite observation provides partial compensation. Remote sensing does not require physical presence, so it bypasses many access restrictions. High-resolution imaging, radar altimetry, and thermal monitoring yield valuable information about ice extent, temperature patterns, and ocean colour. However, satellite data cannot fully replace in situ measurements. Ground calibration remains essential for validating remote observations. Security-related infrastructure can sometimes assist scientific work indirectly. Airfields built for defence purposes occasionally support civilian research flights. Communication networks developed for military reliability may provide backup channels for scientific expeditions. Cooperation agreements formalise these arrangements, though availability varies. Undersea cable routes represent another subtle factor. Communication cables connecting continents sometimes pass through Arctic waters. Protecting these cables involves monitoring zones where anchoring, drilling, or heavy equipment deployment is discouraged. Oceanographic research teams account for cable charts when planning sampling operations. Indigenous communities in Arctic regions also interact with restricted territories. Traditional hunting areas sometimes overlap with military zones. Governments usually consult local communities when establishing restrictions, though concerns still arise. Scientific teams working in partnership with indigenous organisations often gain valuable insights into navigation, wildlife behaviour, and environmental change while respecting cultural practices. Weather monitoring infrastructure maintained for aviation safety can intersect with defence systems. Shared meteorological data improves forecasting accuracy. Scientists benefit from these datasets, though direct access to specific installations may remain controlled. Emergency response coordination represents another point of cooperation. Defence assets, including ice-capable aircraft and ships, occasionally assist civilian rescue operations. Research teams factor potential support availability into risk planning, even if they hope never to need it. Technological evolution gradually changes the landscape. Autonomous sensors reduce the need for large permanent installations. Satellite surveillance capabilities decrease reliance on ground-based radar in some contexts. As these shifts continue, access policies may evolve accordingly, though changes typically occur slowly. Funding agencies recognize these complexities. Grant proposals involving restricted regions often include additional administrative preparation time. Budget allocations account for permit processing, coordination meetings, and compliance documentation. Institutions develop specialized administrative expertise to navigate these requirements efficiently. Researchers themselves rarely view these restrictions as adversarial. Most recognize that national governments balance multiple priorities in polar regions. Open communication usually resolves misunderstandings. Transparency about research goals helps authorities evaluate potential impacts accurately. Occasionally, temporary closures occur for exercises or infrastructure maintenance. These closures are usually announced through maritime or aviation notices. Scientists monitor such notices closely during expedition planning to avoid last-minute disruptions. Public perception sometimes exaggerates the secrecy surrounding Arctic defense zones. While certain operational details remain confidential, general boundaries and purposes are often publicly acknowledged. Academic literature discusses these interactions in practical terms without dramatic interpretation. Academic conferences on polar science sometimes include sessions on regulatory navigation. Researchers share experiences obtaining permits, coordinating with authorities, and integrating compliance into project design. This knowledge exchange reduces duplication of effort across institutions. Environmental monitoring within restricted areas may actually be robust, because defense agencies often maintain long-term observation systems for operational reasons. Where data sharing agreements exist, scientists benefit from continuous datasets that might otherwise be difficult to obtain. Legal frameworks governing Arctic waters continue evolving. Continental shelf claims, maritime boundary agreements, and resource management policies influence how territories are administered. Scientific organizations follow these developments closely because regulatory clarity supports long-term research planning. Climate change introduces additional considerations. As sea ice declines in some regions, shipping routes expand. Increased traffic raises interest in surveillance, safety infrastructure, and environmental monitoring simultaneously. Coordination among stakeholders becomes more complex but also more necessary. Scientific diplomacy plays an important role here. Collaborative research projects often continue even when broader political relations fluctuate. Shared interest in climate data, ecological monitoring, and oceanographic understanding encourages sustained communication channels. Training programs for polar researchers increasingly include regulatory literacy, understanding permitting processes, international maritime law basics, and communication protocols helps field teams operate smoothly within restricted contexts. Technology supporting transparency improves coordination. Digital mapping platforms integrate shipping lanes, environmental zones, and restricted areas into accessible planning tools. Researchers use these platforms early in project design to identify potential constraints. Ethical considerations remain central. Respecting sovereign rights, environmental protection, and community interest aligns with scientific integrity. Responsible conduct builds trust, which can ease future access negotiations. Insurance requirements sometimes reflect restricted zone considerations. Operating near defense infrastructure may involve additional liability clauses. Institutions review these carefully during expedition preparation. Despite all these layers, the overall trend favors gradual expansion of cooperative frameworks. Governments increasingly recognize that understanding Arctic environmental change benefits everyone. Security concerns remain, but they coexist with scientific openness more often than many assume. As access policies evolve, logistical realities continue to matter. Even when administrative approval exists, environmental conditions still dictate feasibility. Researchers therefore evaluate both regulatory and natural constraints together, rather than treating them separately. These human-imposed boundaries add another dimension to the broader picture already discussed. Geography, weather, navigation complexity, and moving ice all interact with administrative factors. None alone explains uneven research coverage, but together they shape where long-term scientific presence becomes practical. From here, attention naturally shifts toward another related influence that often works quietly alongside regulatory constraints: environmental protection policies designed to preserve fragile Arctic ecosystems. Those policies sometimes limit intensive research activity in specific habitats, not to prevent study entirely, but to ensure that scientific presence does not unintentionally damage the very systems researchers aim to understand. When people imagine scientific research in remote places, they often picture scientists going wherever curiosity leads them. In reality, research nearly always operates within regulatory frameworks, and nowhere is that more visible than in the Arctic. Environmental protection rules shape how, when, and sometimes whether scientists can work in specific northern regions. These rules exist for good reason. Arctic ecosystems recover slowly from disturbance. A minor spill, excessive noise, or repeated human presence can produce effects that last far longer than in warmer, more biologically active environments. Because of that, access limitations often reflect caution rather than obstruction, yet they still influence the distribution of scientific knowledge. Arctic wildlife depends heavily on seasonal cycles. Polar bears, seals, walruses, migratory birds, fish populations, and microscopic plankton all follow rhythms tied to ice formation, daylight variation, and ocean productivity. Disturbances during critical periods such as breeding, feeding, or migration can alter behaviour patterns. Environmental regulations therefore restrict certain types of activity during sensitive windows. Aircraft flight altitude minimums may increase during bird nesting seasons. Vessel routes sometimes shift to reduce noise near marine mammal habitats. Researchers accept these conditions as part of responsible fieldwork, even though they may shorten observational windows. Noise management represents a significant regulatory focus. Sound travels efficiently through cold air, and especially through water beneath ice. Marine mammals rely heavily on acoustic communication for navigation, feeding, and social interaction. Scientific sonar surveys, icebreaker engine noise, and aircraft operations all contribute to background sound levels. Regulations may limit sonar intensity, require gradual ramp-up procedures, or restrict operations entirely in certain zones. These precautions protect wildlife, but can delay oceanographic mapping campaigns or underwater vehicle deployment. Pollution prevention rules are particularly strict in polar environments. Fuel handling protocols require secondary containment systems, spill response kits, and trained personnel. Waste management standards prohibit disposal in most circumstances. Everything brought into the field, from packaging to food waste, typically must be removed. These procedures increase logistical complexity. Storage capacity for waste becomes part of expedition planning. Weather delays that postpone waste removal can limit how long research teams remain in place. Chemical sampling studies illustrate another regulatory nuance. Scientists often analyze water, ice, and air samples for trace contaminants. Ironically, the act of sampling must avoid introducing contamination itself. Equipment cleaning standards, sterile handling protocols, and material restrictions are carefully defined. Some protected areas require additional approvals before any physical sample collection occurs, even for scientific purposes. Protected marine zones have expanded gradually across Arctic waters. These zones aim to conserve biodiversity, protect spawning grounds, and maintain ecological resilience. Scientific research within them usually remains permitted but subject to additional review. Proposals must demonstrate minimal disturbance, clear scientific value, and compliance with monitoring requirements. Review committees include environmental scientists as well as regulatory officials. ensuring decisions consider ecological context. Terrestrial Arctic regions, particularly coastal zones and islands, host fragile vegetation communities. Mosses, lichens and tundra plants grow slowly in cold conditions. Foot traffic, vehicle tracks, or temporary structures can leave marks visible for decades. Regulations therefore limit where camps can be established on land. Researchers often use existing disturbed sites rather than creating new ones. Helicopter access reduces ground disturbance but increases fuel consumption and operational cost. Ice-based research carries environmental responsibilities too. Drilling through sea ice requires managing drill fluids carefully. Oceanographic sampling equipment must avoid entangling wildlife. Acoustic deterrent devices used for polar bear safety are regulated to prevent excessive disturbance. Even snow compaction from repeated foot traffic receives attention in sensitive ecological study areas. Environmental impact assessments typically precede major Arctic research projects. These assessments evaluate potential effects on wildlife, vegetation, water quality, cultural heritage sites, and local communities. Mitigation strategies become part of project approval. While assessments add preparation time, they also improve project design by identifying risks early. Indigenous consultation represents another important dimension. Many Arctic regions support indigenous communities with long-standing relationships to local ecosystems. Scientific expeditions consult these communities regarding access routes, wildlife considerations, and cultural sensitivities. Traditional ecological knowledge often improves research quality while ensuring respectful engagement. Regulations formalize this consultation process in many jurisdictions. Climate monitoring programs sometimes face paradoxical restrictions. Studying ice melt, for example, may require placing instruments in areas also designated for wildlife protection. Negotiation between scientific necessity and ecological caution becomes part of planning. Often, compromise solutions emerge, such as seasonal deployment schedules or reduced instrument footprint. Transportation methods fall under environmental scrutiny as well. Icebreaker emissions, aircraft fuel use, and generator exhaust all contribute to local environmental impact. Increasingly, research programs explore alternative energy options, including hybrid power systems, improved insulation reducing heating demand, and more efficient transport scheduling to minimize fuel consumption. Wastewater management illustrates how detailed these regulations can be. Even grey water from cooking or washing cannot always be discharged freely. Treatment systems, storage tanks, and removal protocols must comply with environmental guidelines. These requirements influence camp design and operational duration. Satellite remote sensing helps reduce some physical access needs, yet it introduces its own regulatory considerations. Launch activities, ground station placement, and data sharing agreements all involve environmental and policy frameworks. The shift toward remote observation does not eliminate regulation, it redistributes it. Historical lessons underpin many current rules. Past industrial activities in polar regions, including resource exploration and military operations, occasionally left environmental legacies that required expensive cleanup. Modern regulations aim to prevent similar outcomes. Scientists generally support these measures, recognizing that preserving baseline environmental conditions benefits long-term research. International treaties also play a role. While the Antarctic Treaty System is often cited more prominently, Arctic nations maintain various bilateral and multilateral agreements covering pollution control, wildlife conservation, and maritime safety. These agreements harmonize standards across borders, reducing regulatory conflict while ensuring consistent environmental protection. Research vessel operations illustrate layered compliance. Ships must follow maritime pollution conventions, national environmental laws, and specific Arctic operational guidelines. Crew training includes environmental procedures alongside navigation and safety instruction. Documentation accompanies every voyage detailing fuel management, waste handling, and emergency response readiness. Scientific instrumentation design increasingly reflects environmental priorities. Smaller sensors, biodegradable materials where feasible, and non-invasive sampling techniques reduce ecological footprint. Engineering innovation often stems directly from regulatory requirements, producing tools better suited to fragile ecosystems. Public transparency contributes to regulatory accountability. Many Arctic research projects publish environmental impact summaries alongside scientific results. This openness builds trust with local communities and funding agencies, while demonstrating responsible conduct. Educational outreach connected to environmental protection has grown as well. Students studying polar science learn about ecological ethics early in their training. Understanding regulatory frameworks becomes part of professional competence, rather than an administrative afterthought. Insurance and liability considerations intersect with environmental rules. Accidental damage to protected habitats carries financial consequences. Institutions include environmental compliance in risk assessments, influencing project approval and budgeting. Tourism growth in some Arctic areas has prompted stricter controls that indirectly affect research logistics. Shared infrastructure such as airstrips or ports must balance scientific, commercial and tourism use while maintaining environmental safeguards. Scheduling coordination helps minimize cumulative impact. Climate change introduces new regulatory challenges. As ice retreats, previously inaccessible areas open temporarily. Governments move cautiously before allowing intensive activity in these zones, ensuring protective measures keep pace with environmental change. Scientists sometimes wait for regulatory clarity before initiating new studies. Data stewardship also reflects environmental ethics. Sharing ecological data responsibly helps conservation planning. Collaborative databases allow scientists and policymakers to monitor ecosystem health collectively, reinforcing the value of regulated research access. Technological monitoring supports enforcement, satellite tracking of vessel movements, automatic identification systems, and environmental sensors help authorities verify compliance. These tools reduce the need for on-site inspection while maintaining oversight. Researchers often describe environmental regulation not as restriction, but as structure. Clear guidelines help avoid accidental harm and clarify expectations. While administrative effort increases, scientific credibility benefits from demonstrable responsibility. Long-term ecological monitoring programs sometimes gain privileged access precisely because they support conservation goals. These programs operate under strict protocols but contribute valuable baseline data that informs policy decisions. Interdisciplinary collaboration strengthens regulatory navigation. Environmental lawyers, policy experts, ecologists, and engineers work alongside field scientists to design compliant research strategies. This teamwork reduces delays and improves project resilience. Environmental ethics discussions increasingly include carbon footprint considerations. Arctic research, by nature logistically intensive, generates emissions. Institutions explore carbon offset programs, efficiency improvements, and alternative fuels where practical. Even seemingly minor details, such as food sourcing for expeditions, receive attention. Minimizing packaging waste, avoiding invasive species transport, and managing organic waste responsibly all reflect broader environmental priorities. Scientific culture continues evolving towards sustainability awareness. Younger researchers often enter the field already familiar with environmental compliance principles. This generational shift streamlines future project planning. These environmental protection measures explain why certain Arctic locations experience limited direct research presence despite scientific interest. The goal is not to prevent study, but to ensure that investigation does not compromise the ecosystems being studied. As research planning balances environmental responsibility with scientific curiosity, another practical constraint frequently comes into focus as well: the significant financial cost of operating safely in polar environments. Those economic considerations influence how often expeditions occur, how long they remain in the field, and which regions receive sustained observation. If you talk to people who have actually worked in Arctic research, one theme comes up quickly and consistently. It is not always the cold, the darkness, or even the technical difficulty that determines how much science gets done near the North Pole. Very often it is cost. Not just ordinary research funding levels, but the kind of sustained financial commitment that only large national agencies, multinational collaborations, or very well-funded institutions can realistically maintain. The price of operating safely and effectively in that environment shapes which projects happen, how often they happen, and how long they continue. Transport alone accounts for a large share of the expense. Getting people and equipment into central Arctic regions typically requires specialised aircraft, icebreakers, or both. Icebreaker vessels are among the most expensive ships to operate. Their reinforced hulls, powerful engines, experienced crews, and fuel consumption all contribute to operating costs that far exceed those of standard research vessels. Even a single expedition can cost millions in fuel, crew time, maintenance, and logistical support. Because of that, many institutions cannot justify frequent voyages, so opportunities for direct field research remain limited. Aircraft operations carry similar financial weight. Cargo planes capable of landing on ice require specialised modifications, experienced polar pilots, and carefully prepared landing strips. Fuel must often be transported in advance and stored safely under extreme conditions. Weather delays can extend aircraft standby time, which increases cost without producing additional research output. Every flight window therefore represents a significant investment that planners try to maximise. Equipment transportation adds another layer. Scientific instruments designed for temperate environments often need cold weather modifications. Insulated casings, reinforced materials, and redundancy systems increase weight and price. Heavy or delicate instruments may require dedicated cargo flights rather than shared transport, which raises costs further. Spare parts must accompany most equipment, because replacement deliveries may not be possible quickly. Field accommodation expenses are easy to underestimate. Temporary camps require heated shelters, generators, food supplies, medical kits, communication systems, and waste storage infrastructure. These are not optional comforts. They are essential for safety. Maintaining a small team for several months involves continuous resupply planning and fuel management. Heating alone consumes substantial energy, because temperatures remain far below freezing much of the year. Personnel training represents another cost category that is often invisible to the public. Polar researchers undergo specialised preparation covering cold weather survival, emergency medical response, wildlife safety, navigation and equipment operation. Training programs take time and resources. Institutions cannot send unprepared teams into such environments without increasing risk significantly. Insurance providers often require documented training before approving coverage. Insurance itself can be expensive. Operating in remote, hazardous environments increases liability considerations. Coverage must include evacuation scenarios, equipment loss, environmental protection compliance, and sometimes geopolitical risk depending on expedition location. These policies ensure safety nets exist, but they also add to overall project budgets. Communication infrastructure expenses have grown alongside technological expectations. Reliable satellite communication allows real-time data transmission, safety monitoring, and coordination with support teams. High-latitude bandwidth remains costly. Expeditions budget for dedicated communication time, backup systems, and technical support. Data-intensive projects such as high-resolution imaging or continuous sensor networks must factor communication cost carefully into planning. Energy supply solutions increasingly attract attention as institutions try to balance cost with environmental responsibility. Traditional diesel generators remain common, Yet transporting fuel to remote ice camps is expensive and environmentally sensitive. Hybrid systems incorporating wind turbines or solar panels help reduce fuel consumption, but require initial capital investment and engineering expertise. Long-term cost savings sometimes justify these systems, though upfront expense can still limit adoption. Maintenance cycles in the Arctic differ from those elsewhere. Equipment exposed to extreme cold experiences accelerated wear in certain components. Seals harden, lubricants thicken, electronics stress differently. Regular inspection and replacement schedules prevent failures but increase operational cost. Losing a critical instrument mid-expedition can compromise an entire data set, so preventive maintenance remains essential. Opportunity cost influences institutional decisions too. Funding allocated to polar research cannot simultaneously support other projects. Agencies evaluate expected scientific return carefully. Regions offering easier access or faster data collection sometimes receive priority simply because they allow more efficient use of limited funds. This pragmatic approach explains some geographic unevenness in research coverage. International collaboration helps distribute costs, but coordination introduces administrative complexity. Shared expeditions require agreement on funding contributions, research priorities, data sharing policies, and operational leadership. Negotiations take time. Currency fluctuations, budget cycles, and political changes can influence commitments unexpectedly. Long-term monitoring programs illustrate the financial challenge clearly. Climate studies benefit from decades of continuous observation, maintaining instruments, replacing aging hardware, and funding field visits year after year requires sustained commitment. Some programs succeed through stable government funding. Others rely on grant cycles that create uncertainty. Interruptions due to funding gaps contribute to data discontinuity. Technological innovation sometimes reduces cost gradually. Smaller sensors, more efficient power systems, and autonomous platforms lower operational expense. However, developing those technologies requires initial investment. Early adopters often pay higher prices until production scales up. Autonomous vehicles, for example, can operate under ice or across its surface without continuous human presence. They reduce accommodation costs and some transport requirements, yet they still require deployment missions, maintenance planning, and recovery operations. Reliability testing in extreme conditions also adds development expense. Fuel price volatility influences expedition budgets significantly. Arctic operations consume large fuel quantities. Global energy market changes therefore ripple directly into research planning. Projects scheduled years in advance must include contingency funds to absorb price fluctuations. Regulatory compliance costs intersect with logistics as well. Environmental impact assessments, permit processing, and monitoring requirements all involve administrative effort and sometimes consulting services. These expenses support responsible research but still affect total project budgets. Institutional infrastructure investment shapes long-term capability. Countries with established Arctic research stations, icebreaker fleets, and trained personnel maintain ongoing presence more easily. Institutions without such infrastructure face higher entry costs. Building capacity takes years and consistent funding. Public funding priorities shift over time. Economic conditions, political leadership, and societal interest influence budget allocation. Polar research competes with healthcare, education, infrastructure, and other scientific fields. Advocates emphasize the global importance of Arctic climate understanding, but funding levels still fluctuate. Private sector partnerships occasionally offset costs. Energy companies, technology firms, and philanthropic organizations sometimes support polar research, aligned with their interests. These partnerships can accelerate specific projects while raising questions about data ownership and research independence. Clear agreements help maintain scientific integrity. Educational institutions play a role by training future researchers who may work within larger national programs. Student involvement lowers some labour costs while providing valuable experience. However, supervision requirements ensure experienced personnel remain central to operations. Logistics planning includes redundancy budgeting, spare equipment, backup communication systems, additional fuel reserves, and contingency transport options all cost money. Removing redundancy saves funds initially but increases risk. Most polar programs err on the side of caution. Weather delays translate directly into financial impact. Chartering aircraft or ships involves daily operating costs even when missions pause. Insurance, crew wages, and equipment leasing continue regardless of productivity. Flexible scheduling mitigates some losses, though unpredictability remains. Supply chain coordination deserves mention too. Specialized cold weather equipment often comes from limited manufacturers. Production delays, shipping constraints, or regulatory inspections can postpone expeditions. Planning buffers help but require early commitment of funds. Medical preparedness includes evacuation insurance, telemedicine capability, and trained medical personnel. These safeguards protect human life but add operational cost. Remote medical incidents carry high logistical expense, reinforcing the importance of preventive measures. Data management infrastructure also requires investment. Storing large data sets, maintaining secure backups, and supporting collaborative analysis platforms cost money beyond field operations. Long-term archival commitments ensure data remains accessible for future research. Despite all these expenses, institutions continue funding Arctic research because of its global significance. Climate feedback loops, ocean circulation, biodiversity trends, and atmospheric dynamics studied there influence weather and ecosystems worldwide. Cost-benefit evaluations increasingly account for these broader impacts. Efficiency improvements accumulate slowly. Shared expeditions reduce duplication. Standardized equipment lowers procurement cost. Digital planning tools optimize logistics. Over time, these incremental gains expand research capacity modestly. Still, the reality remains that sustained Arctic research demands financial resources not every institution possesses. As a result, some areas receive periodic study rather than continuous observation. Data gaps reflect economic practicality as much as environmental difficulty. Understanding the cost dimension clarifies why scientific coverage across the North Pole region appears uneven. It is not simply a matter of curiosity or capability. Budgetary sustainability shapes research geography in ways often invisible outside the scientific community. Those financial constraints interact closely with technical limitations too. Even when funding exists, equipment performance in extreme cold introduces additional challenges. Mechanical reliability, electronic stability, and material durability all influence operational success, which naturally leads toward examining how equipment failures themselves shape research planning in the far north. If you have ever noticed how a phone battery drains faster on a cold winter day, you already have a small preview of a much larger issue that scientists face in polar research. Equipment that works reliably in moderate climates often behaves very differently when exposed to sustained Arctic temperatures. Near the North Pole, it is not unusual for air temperatures to remain far below freezing for extended periods. That environment affects mechanical systems, electronics, materials, and even simple everyday tools in ways that require constant attention. Equipment failure is not an occasional inconvenience there. It is an expected part of operations, and it shapes how research projects are designed from the very beginning. Cold affects batteries first and most noticeably. Chemical reactions inside batteries slow significantly at low temperatures. Voltage output drops, effective capacity shrinks, and recharge cycles become less efficient. Devices that normally run for hours may shut down quickly. Scientists compensate by using insulated battery enclosures, chemical heat packs, or internal heating elements powered by the batteries themselves. That approach keeps systems operational but consumes additional energy. which in turn increases fuel requirements for generators or replacement battery shipments. Lubricants present another challenge. Oils and greases that keep mechanical parts moving smoothly thicken in cold conditions. Increased viscosity leads to higher friction, slower response times, and sometimes complete mechanical seizure. Equipment designed for polar use relies on specially formulated lubricants, yet even these have performance limits. Moving parts in drilling rigs, robotic arms, camera mounts, and vehicle engines require regular inspection to prevent unexpected failure. Metal fatigue behaves differently in cold environments as well. Many metals become more brittle at low temperatures. Components that flex repeatedly, such as hinges, brackets, or cable connectors, may crack after extended exposure. Engineers select alloys known for better cold tolerance, but monitoring remains essential. Replacement parts must accompany expeditions because field repair opportunities are limited. Plastics and polymers experience similar brittleness issues. Cable insulation can crack. Protective housings may fracture under minor impact. Even simple items such as zip ties or protective covers require cold-rated versions. These details seem small individually, but they accumulate across an entire research station, influencing overall reliability. Electronic displays behave differently too. Liquid crystal displays respond slowly in cold temperatures. Screens may appear dim, blurred, or temporarily unresponsive. Researchers often keep sensitive electronics inside heated enclosures when not in use. This practice reduces exposure time but adds logistical complexity when equipment must be deployed frequently. Condensation and frost present additional complications. Moving equipment between heated shelters and outdoor cold environments causes moisture to condense and freeze on surfaces. Frost buildup interferes with sensors, optics, connectors, and ventilation systems. Scientists develop strict acclimatization procedures, allowing equipment to cool gradually before use to reduce condensation risk. Optical instruments require particular care. Cameras, spectrometers, and telescopes rely on clear lenses and stable alignment. Frost formation or thermal contraction can alter calibration. Protective lens heaters, anti-fog coatings, and sealed housings help maintain performance, though they increase power consumption. Cables stiffen in cold temperatures, reducing flexibility and increasing fracture risk during handling. Data cables, power lines, and communication wiring must use cold-rated insulation materials. Routing these cables requires careful planning to avoid sharp bends that could cause cracks over time. Computing hardware encounters its own challenges. Hard drives historically struggled with low temperatures due to mechanical components. Solid-state drives perform better, but extreme cold still influences electronic stability. Researchers use ruggedized computers designed specifically for polar conditions. Backup systems remain standard because data loss risk never disappears entirely. Sensors designed to measure environmental variables sometimes face paradoxical issues. Thermometers must measure cold accurately without being affected by it structurally. Pressure sensors, humidity detectors, and gas analyzers require calibration protocols adapted to extreme conditions. Regular recalibration becomes routine fieldwork. Communications equipment can be particularly sensitive. Antennas accumulate ice, affecting signal strength. Connectors contract slightly with temperature changes, altering electrical contact quality. Heated antenna mounts and weatherproof connectors help maintain reliability, though maintenance checks remain frequent. Vehicle reliability illustrates cold effects clearly. Snowmobiles, tracked vehicles, and ice-capable trucks require preheating before operation. Fuel systems use additives to prevent gelling. Engine fluids require specialized formulations. Spare parts inventories grow accordingly because repair facilities are far away. Aircraft operations also account for cold-related equipment issues. Hydraulic systems, avionics, and structural materials all require cold weather certification. Pre-flight inspections include checks specific to polar conditions. Delays for maintenance or warming procedures become routine rather than exceptional. Scientific drilling equipment experiences stress from both cold air and ice interaction. Drill bits encounter variable ice hardness. Hydraulic systems must maintain consistent pressure despite temperature-induced fluid, viscosity changes. Operators adjust procedures continuously based on conditions. Power generation infrastructure remains a constant focus. Diesel generators must start reliably in low temperatures. Fuel storage tanks require insulation and monitoring. Backup generators ensure redundancy because losing power affects heating, communications, and instrument operation simultaneously. Autonomous instruments deployed on ice or underwater face long-term exposure without direct maintenance. Engineers design them with minimal moving parts, robust housings, and energy-efficient operation. Even so, failure rates remain higher than in temperate deployments. Data recovery strategies assume some losses. Calibration drift occurs subtly over time. Temperature cycling, mechanical stress, and environmental exposure shift instrument baselines. Regular calibration checks maintain data quality, though these checks require time, trained personnel, and sometimes additional equipment. Protective clothing and personal gear for researchers also fall into the equipment category. Gloves must allow dexterity while maintaining insulation. Face protection prevents frostbite during instrument handling. These requirements influence how quickly and accurately tasks can be performed outdoors. Material science research continues addressing these challenges. New composites, improved battery chemistries, advanced insulation materials, and cold-resistant electronics gradually enhance reliability. Adoption takes time because field validation under real conditions remains essential. Field improvisation sometimes becomes necessary despite preparation. Engineers and scientists carry repair kits, spare fasteners, sealing compounds, and diagnostic tools. Creativity helps solve unexpected problems, though safety considerations always guide improvisation limits. Training emphasizes preventive maintenance. Researchers learn to inspect seals, clean connectors, monitor battery performance, and recognize early signs of mechanical stress. Catching issues early prevents cascading failures. Data redundancy strategies mitigate equipment risk. Instruments often record locally even while transmitting data remotely. Multiple sensors measure the same variable in critical experiments. If one unit fails, others preserve continuity. Environmental ethics influence equipment choice as well. Durable equipment reduces waste. Energy-efficient designs minimize fuel transport needs. Environmental regulations sometimes require specific material standards to prevent contamination. Funding considerations tie closely to equipment reliability. High-quality cold-rated instruments cost more initially, but reduce replacement frequency. Institutions weigh upfront expense against long-term operational stability. Supply chain planning ensures spare parts availability. Replacement shipments to polar regions take time. Field teams carry more spares than typical research projects would require elsewhere. Collaboration between engineers and scientists continues strengthening. Equipment design increasingly incorporates direct field feedback. Iterative improvement cycles reflect real-world experience rather than purely laboratory testing. Remote diagnostics have improved maintenance efficiency. Sensors monitor internal equipment health, transmitting alerts before failures occur. Predictive maintenance reduces downtime, though communication bandwidth limits still apply. Public awareness of these technical challenges remains limited. Media coverage of polar research often highlights environmental findings rather than operational details. Yet these technical realities shape what science becomes possible. Despite persistent challenges, reliability has improved over decades. Earlier expeditions faced higher failure rates with less sophisticated materials. Modern engineering combined with experience has significantly enhanced operational success. Still, equipment vulnerability remains part of polar research culture. Teams expect setbacks and plan accordingly. Flexibility, redundancy, and patience characterize successful operations. Understanding how ultra-cold conditions affect equipment clarifies why long-term research near the North Pole progresses steadily but cautiously. Technical capability exists, yet maintaining reliability demands careful design, funding, and operational discipline. These equipment realities also intersect with observational technology more broadly. Satellite monitoring, remote sensing platforms, and autonomous observation networks play growing roles precisely because they reduce dependence on fragile ground equipment, which naturally leads toward examining how satellite observation itself faces limitations near the pole despite technological progress. From a distance, it often seems as though satellites have solved the problem of remote observation. Weather forecasts, navigation apps, environmental monitoring dashboards all rely heavily on data collected far above Earth's surface. So it might sound surprising that even with dozens of orbiting platforms, observation near the North Pole still carries noticeable limitations. Satellites provide essential information, yet they do not eliminate uncertainty entirely. Their orbital geometry, sensor physics, environmental interference, and data processing challenges combine in ways that leave some polar measurements less complete than people expect. Orbital mechanics sits at the center of the issue. Many communication and observation satellites occupy geostationary orbits, meaning they remain fixed relative to a point near Earth's equator. From that position, they see large portions of the planet continuously. Near the poles, however, their viewing angle becomes extremely shallow or disappears entirely below the horizon. That geometry reduces image quality, increases atmospheric distortion, and sometimes prevents coverage altogether. For this reason, geostationary satellites contribute less to polar monitoring than they do elsewhere. Polar orbiting satellites address this gap by travelling north-south across Earth rather than circling the equator. Over time, Earth's rotation allows these satellites to scan nearly the entire surface. They are indispensable for Arctic observation, especially for sea ice extent, temperature mapping, and atmospheric profiling. Even so, they do not hover continuously over one spot. Instead, they pass overhead periodically. Depending on orbit parameters, a specific location near the pole might be observed multiple times per day, but not constantly. Rapid environmental changes between passes can go undetected temporarily. Cloud cover introduces another complication. Optical sensors rely on visible or infrared light reflected from Earth's surface. Arctic weather frequently includes low cloud layers, fog, or blowing snow. These conditions obscure surface features. Synthetic aperture radar systems overcome some of this limitation, because they penetrate clouds and operate regardless of daylight. However, radar data requires specialized interpretation. Surface roughness, moisture content, and ice structure all influence radar backscatter in complex ways. Seasonal darkness affects optical sensing further. During polar night, visible light imaging becomes impossible. Infrared sensors continue functioning, but temperature contrast between surface features may decrease during prolonged cold periods. Identifying details such as thin ice leads, snow accumulation patterns, or wildlife presence becomes more challenging without daylight. Surface reflectivity plays a subtle but important role. Snow and ice reflect large amounts of solar radiation. This high albedo can saturate optical sensors or reduce contrast between adjacent features. Calibration procedures compensate, though some detail loss remains inevitable. Researchers combine multiple sensor types to improve accuracy. Sea ice thickness measurement illustrates combined limitations clearly. Satellites estimate thickness indirectly by measuring freeboard, the portion of ice above water level. That measurement depends on assumptions about snow depth, ice density, and water salinity. Variability in these parameters introduces uncertainty. Ground measurements help calibrate satellite estimates, but those ground observations are themselves limited by logistics discussed earlier. communication satellites face similar geometric constraints. Signal paths near the pole often travel longer atmospheric distances at shallow angles. This geometry increases signal attenuation and susceptibility to interference. New satellite constellations designed with higher inclination orbits improve coverage, yet capacity and bandwidth limitations persist. Atmospheric research relies heavily on satellite instruments measuring temperature, humidity, ozone concentration, and aerosol content. Polar atmospheric conditions, including temperature inversions and unique circulation patterns, complicate retrieval algorithms. Data processing models originally developed for mid-latitudes sometimes require adjustment to maintain accuracy at high latitudes. Magnetic field interactions can influence certain satellite measurements as well. The auroral oval, where charged particles interact with Earth's magnetic field, lies near polar regions. These interactions affect ionospheric conditions, occasionally disrupting radio signal propagation and influencing some remote sensing techniques. Temporal resolution remains another limitation. Even frequent satellite passes cannot match continuous ground-based observation. Weather events, ice-cracking episodes, or short-lived biological phenomena may occur between overpasses. Scientists supplement satellite data with autonomous ground instruments where possible, though those instruments face the environmental challenges already discussed. Data transmission from polar satellites requires ground stations positioned strategically. Some ground stations operate in high-latitude locations specifically for this purpose. Weather conditions, maintenance needs, and communication infrastructure influence how quickly satellite data becomes available for analysis. Latency can matter for operational forecasting. Resolution trade-offs also shape observation capability. High-resolution imagery typically covers smaller areas per pass, while wide-area scans provide lower spatial detail. Designing satellite missions involves balancing these competing priorities. Arctic researchers sometimes wish for both simultaneously, which current technology cannot always deliver. Calibration and validation remain essential. Satellite sensors drift over time due to radiation exposure, thermal cycling, and aging electronics. Regular comparison with ground truth data maintains reliability. Limited ground access near the pole therefore indirectly affects satellite data accuracy. Ice edge detection presents a practical example. Satellite imagery identifies the boundary between open water and ice cover. However, slush zones, thin new ice, or melt ponds complicate classification. Algorithms improve continually, but uncertainty remains higher than in open ocean mapping. Biological observation from space faces additional constraints. Phytoplankton blooms can sometimes be detected through ocean color analysis, but ice cover, cloudiness, and low sun angles reduce signal clarity. Wildlife tracking from space relies on tagged individuals rather than direct imaging in most cases. Thermal measurements provide valuable climate data, yet surface temperature interpretation under snow cover involves modelling assumptions. Snow insulates underlying ice or water, influencing apparent temperature readings. Researchers integrate multiple data sources to refine interpretations. Satellite lifetime and maintenance considerations also play a role. Unlike ground instruments, satellites cannot easily be repaired once launched. Mission planning includes redundancy, but unexpected failures still occur. Replacement missions require years of development. Cost influences satellite coverage as well. Launch expenses, instrument development, and operational support require substantial funding. Agencies prioritize mission objectives carefully. Arctic observation competes with other global monitoring needs. International cooperation improves coverage. Data sharing agreements among space agencies allow broader access to multiple satellite datasets. Collaborative missions reduce duplication and enhance overall observational capability. Technological innovation continues steadily. Improved sensor sensitivity, higher bandwidth communication links, and more flexible satellite constellations gradually reduce observation gaps. CubeSat deployments provide cost-effective supplementary coverage, though they typically offer lower instrument capability. Artificial intelligence increasingly assists data processing. Machine learning algorithms help distinguish ice types, identify cloud patterns, and detect subtle environmental changes. These tools enhance interpretation, but still rely on high-quality input data. Public accessibility to satellite data has improved significantly. Open data policies allow researchers worldwide to analyze Arctic conditions without direct field presence. This democratization accelerates scientific collaboration. Despite these advances, satellites complement rather than replace in situ research. Direct measurements remain necessary for calibration, detailed sampling, and process-level understanding. Both approaches function best together. Educational outreach helps communicate these nuances. Public perception often assumes satellites see everything clearly at all times. Explaining limitations builds realistic expectations about scientific certainty. Climate change monitoring illustrates the combined approach. Satellite data shows large-scale trends in ice extent and temperature. Ground measurements reveal detailed mechanisms driving those trends. Integration strengthens conclusions. Operational forecasting benefits from satellite observation despite limitations. Ice navigation advisories, weather predictions, and environmental alerts rely heavily on orbital data. Continuous improvement enhances safety for shipping and research expeditions alike. Looking ahead, new satellite architectures promise improved polar coverage. Highly elliptical orbits designed specifically for high-latitude observation are under consideration. These orbits would provide longer dwell time over polar regions. As satellite capability evolves, ground research planning adapts accordingly. Some measurements shift toward remote observation, while others remain field-dependent. The balance changes gradually rather than abruptly. Understanding satellite observation limits clarifies why some polar scientific questions remain partially answered. Technology provides remarkable reach, yet physical constraints, environmental interference, and economic considerations still shape what can be observed consistently. These observational realities connect naturally with another aspect of Arctic fieldwork already hinted at earlier, the interaction between researchers and wildlife. Polar ecosystems host species adapted to extreme conditions, and their presence influences where scientists can safely operate and how fieldwork is conducted over extended periods. When conversations turn to Arctic research challenges, people often think first about ice, weather, or technology. Wildlife tends to enter the discussion later, sometimes almost as an afterthought. Yet researchers who spend extended time in the far north treat wildlife awareness as a routine and serious part of field preparation. Not because encounters happen constantly, but because when they do occur, they can escalate quickly. The Arctic is home to animals that are well adapted to harsh conditions, highly mobile across ice and ocean, and sometimes curious about unfamiliar human activity. Scientists approach this reality with respect rather than fear, building practical safety protocols into daily operations. Polar bears usually come to mind first, and for understandable reasons. They are apex predators in the Arctic ecosystem, strong swimmers, capable travelers across sea ice, and highly sensitive to scent. Research camps, even those carefully managed, produce odors from food, fuel, and human presence. Bears occasionally investigate out of curiosity or hunger. Most encounters end without incident because researchers maintain awareness, but preparation remains essential. Camps establish watch rotations, particularly during low visibility conditions. Deterrent tools, such as noise devices or non-lethal flare systems, remain standard equipment. Lethal force is considered only as a last resort because conservation ethics strongly discourage harm whenever possible. Food storage procedures reflect this risk. Supplies are sealed in odor-resistant containers and stored at controlled distances from sleeping areas. Waste management becomes part of wildlife safety as well as environmental protection. Leaving organic waste exposed increases the chance of attracting animals. Field teams remove waste regularly, or store it securely until transport becomes possible. Seals and walruses present a different kind of consideration. They're generally not aggressive toward humans, but they occupy breathing holes in ice and haul out sites along ice edges or coastal areas. Disturbing these sites can disrupt feeding and resting behaviour. Regulations often specify minimum approach distances. Researchers studying marine mammals typically use observation techniques designed to minimise stress, such as remote cameras, acoustic monitoring, or aerial surveys conducted at appropriate altitudes. Bird colonies create another set of practical constraints. Arctic coastal cliffs and tundra zones host seasonal nesting sites for migratory birds. Aircraft noise, repeated foot traffic, or equipment placement near nesting grounds can affect breeding success. Environmental guidelines restrict access during sensitive periods. Researchers plan fieldwork timing accordingly, even when those windows coincide with optimal weather conditions. Marine mammals beneath the ice introduce subtler operational concerns. Sonar systems used for oceanographic mapping must account for acoustic sensitivity of whales and seals. Gradual power ramp-up procedures allow animals time to move away before full-strength signals begin. These protocols reduce disturbance while allowing scientific measurement to continue. Foxes, while smaller than polar bears, sometimes approach camps searching for food. They're generally cautious but adaptable. Proper food storage prevents habituation. Researchers avoid feeding wildlife intentionally because conditioned animals lose natural avoidance behaviours which can create future risk. Mosquitoes and biting insects might sound minor compared with large mammals, yet they influence field operations significantly during summer months. Dense swarms occur in certain coastal and tundra regions. Protective clothing, netting, and repellents become essential. Extended exposure affects concentration and comfort, which indirectly influences research productivity. Underwater ecosystems present their own interactions. Fish populations, plankton blooms, and benthic organisms form part of ongoing study. Sampling methods must minimize habitat disruption. Environmental review boards assess proposed techniques to ensure ecological balance remains intact. Ice-dependent wildlife responds to environmental change as well. Thinner ice affects hunting patterns for polar bears, migration timing for seals, and breeding locations for certain birds. Researchers monitoring climate change often observe these behavioral shifts directly. Field safety planning adapts accordingly because historical encounter patterns may no longer apply consistently. Training programs for polar researchers include wildlife awareness modules. Participants learn species identification, behavior patterns, deterrent techniques, and emergency response procedures. Training emphasizes avoidance first, deterrence second, and emergency measures only if necessary. This structured approach reduces incident probability. Technological tools assist with monitoring. Motion sensors, remote cameras, and radar systems sometimes supplement human observation. These tools provide early warning of approaching animals, especially during low visibility or polar night conditions. Integrating technology with traditional watch rotations enhances safety. Communication protocols within camps reinforce awareness. Researchers check in regularly when working away from main shelters. Buddy systems ensure individuals rarely operate alone in areas where wildlife presence is possible. Radios remain standard equipment for field excursions. Insurance policies often require documented wildlife safety procedures. Institutions demonstrate training, equipment availability, and emergency planning before expeditions receive approval. These requirements align with both safety and ethical considerations. Indigenous knowledge contributes significantly to wildlife understanding. Local communities possess generations of experience observing animal movement, seasonal behavior, and environmental indicators. Collaborative research projects often incorporate this knowledge, improving both safety and scientific insight. Wildlife encounters sometimes influence research site selection directly. Areas known for high polar bear activity or sensitive breeding grounds may be avoided unless study objectives specifically involve those species. Even then, specialized safety planning becomes part of project design. Lighting strategies during polar night help maintain awareness. Exterior illumination around camps reduces surprise encounters. However, lighting must balance safety with energy consumption and potential disturbance to wildlife. Engineers design efficient systems tailored to these constraints. Waste heat from generators or shelters can attract curious animals seeking warmth. Camp layout planning considers this possibility. Equipment placement minimizes accessible sheltered spaces where animals might linger. Emergency response planning includes wildlife scenarios. First aid training covers bite and injury management. Evacuation plans consider the possibility of delayed response due to weather or remoteness. Preparedness reduces risk even though serious incidents remain rare. Research ethics emphasize minimizing wildlife disturbance not only for safety but for data integrity. Animals behaving naturally provide more reliable ecological information. Excessive human presence alters behavior, complicating interpretation. Acoustic monitoring of wildlife helps assess population health. Passive listening devices capture vocalizations without requiring close human presence. These methods expand data collection while reducing interaction risk. Public interest in Arctic wildlife often focuses on iconic species, especially polar bears. Scientists balance outreach with realism, emphasizing respect rather than sensationalism. Accurate portrayal supports conservation goals. Climate policy discussions increasingly incorporate wildlife data gathered by researchers. Habitat change, migration shifts, and population trends inform environmental management decisions. Field observations contribute essential evidence. Technological innovation continues supporting safer observation. Long-range cameras, drones, and autonomous monitoring stations reduce the need for close physical presence. Adoption grows gradually as reliability improves. Safety culture within polar research emphasizes humility. Experienced researchers acknowledge that wildlife behavior can be unpredictable. Continuous vigilance remains standard practice regardless of prior experience. Data recording includes wildlife observations even when not central to project goals. Unexpected sightings contribute to broader ecological databases. These incidental records sometimes reveal emerging trends. Collaboration with conservation organizations strengthens both safety and scientific outcomes. Shared protocols, training resources, and data exchange improve overall effectiveness. Public misconceptions occasionally exaggerate wildlife danger. Most Arctic research proceeds without incident because preparation, awareness, and respect guide operations. Still, the potential risk shapes planning quietly in the background. Understanding wildlife considerations helps explain why certain Arctic areas see intermittent research presence. Safety planning requires resources, training, and infrastructure that not every project can support continuously. These biological factors intersect with psychological ones as well. Extended isolation combined with constant environmental awareness influences researcher well-being over time, which naturally connects to another aspect of Arctic fieldwork that receives increasing attention: the mental and emotional effects of prolonged polar isolation on scientific teams. When people picture Arctic research, they often imagine physical hardship first. Cold temperatures, heavy equipment, long travel distances, those are easy to visualize. What tends to receive less attention is the psychological side of working in extreme isolation. Scientists heading north usually prepare extensively for environmental hazards, yet the mental adjustment to prolonged remoteness, confined living spaces, unusual light cycles, and limited social variety can be just as demanding. It rarely becomes dramatic enough to stop research outright, but it quietly shapes how long teams can stay, how effectively they work, and how future expeditions are planned. Isolation in the Arctic is not simply about distance from cities. It is about being removed from normal routines. Communication with family and colleagues may depend on satellite links that occasionally drop out. News from the outside world arrives intermittently. personal privacy becomes limited when small teams share compact shelters for weeks or months. These conditions are manageable, yet they require conscious adaptation. Light cycles play a significant role in psychological well-being. During summer, continuous daylight disrupts sleep patterns. Blackout curtains help, but circadian rhythms still shift. Some researchers report difficulty falling asleep or maintaining consistent rest schedules. During winter, the opposite occurs. Extended darkness affects alertness and mood. Light therapy lamps and structured daily routines help stabilize biological rhythms, though adjustment takes time each season. Monotony contributes in quieter ways. Arctic landscapes can appear visually uniform, especially when snow cover stretches uninterrupted across the horizon. The lack of varied scenery reduces sensory stimulation. Indoors, limited recreational options reinforce routine repetition. Researchers often bring books, films, musical instruments, exercise equipment, or hobby supplies to maintain mental engagement during downtime. Team dynamics become especially important in these environments. Small groups live and work closely together, often with little opportunity for personal space. Minor disagreements that might fade quickly elsewhere can feel amplified. Training in communication, conflict resolution, and group cohesion has therefore become standard in many polar research programs. Institutions recognize that interpersonal stability directly supports scientific productivity. Work-life boundaries blur easily. When laboratory, office, and living quarters share the same structure, switching mentally between professional tasks and relaxation requires conscious effort. Some teams establish scheduled communal meals, shared recreational time, or quiet hours to maintain balance. Stress management techniques vary. Regular physical activity helps counter sedentary periods caused by weather restrictions. Exercise also supports sleep regulation and mood stability. Many stations include compact gyms or designated exercise areas for this reason. Psychological screening sometimes precedes long-term deployments. The goal is not exclusion, but preparation. Understanding individual coping styles helps team leaders assign roles and support structures effectively. Ongoing mental health support, including remote counseling availability, has become more common as awareness grows. Cognitive performance can shift subtly under isolation. Concentration, reaction time, and decision-making may fluctuate, especially during polar night. Researchers design operational procedures with redundancy and peer verification to reduce error risk. These safeguards benefit safety and data integrity. Connection with the outside world remains essential. Scheduled communication sessions with family, institutional colleagues, or support teams help maintain perspective. Reliable communication infrastructure therefore serves psychological as well as operational needs. Cultural diversity within teams adds both richness and complexity. International collaborations bring varied communication styles, expectations, and coping strategies. Pre-expedition orientation sessions help align expectations and foster mutual understanding. Environmental awareness never fully switches off. Even during rest periods, researchers remain conscious of weather changes, wildlife presence, and equipment status. This continuous low-level vigilance contributes to mental fatigue over time. Rotating responsibilities and scheduled downtime mitigate the effect. Personal milestones occurring during deployments, birthdays, holidays, family events can intensify feelings of separation. Teams often organize shared celebrations to maintain morale. Small traditions help create a sense of continuity. Experience level influences adjustment. First-time polar researchers typically need more adaptation time. Veterans develop routines and expectations that reduce uncertainty. Mentorship programs pair experienced personnel with newcomers to support transition. Unexpected events test resilience. Equipment failures, weather delays, or logistical setbacks can disrupt planned schedules. Maintaining flexibility becomes a psychological skill as much as a practical necessity. teams that view setbacks as routine rather than exceptional cope more smoothly. Research on isolation in space missions and submarines provides useful parallels. Controlled environments, limited external contact, and confined living conditions share similarities with polar stations. Insights from those fields inform polar expedition preparation. Nutrition plays a supporting role. Balanced diets help maintain energy and mood stability. Fresh food availability varies depending on resupply schedules. Some stations experiment with small hydroponic gardens to supplement supplies, providing both nutrition and psychological benefit. Sleep quality receives particular attention. Noise from generators, heating systems, or weather conditions can interfere with rest. Ear protection, soundproofing improvements, and consistent schedules help mitigate disturbances. Mindfulness and relaxation practices have gained acceptance in polar programs. Techniques such as breathing exercises, meditation, or structured reflection support stress management. These practices require minimal equipment and adapt well to remote settings. Journaling remains popular among researchers. Recording daily experiences helps process isolation and track emotional patterns. Some journals later contribute to public outreach or academic study of polar psychology. Digital entertainment provides connection, but also presents balance challenges. Continuous online engagement can blur time perception further. Teams encourage moderate use alongside offline activities. Leadership style influences psychological climate significantly. Supportive leadership, clear communication, and fair workload distribution foster resilience. Institutions increasingly train expedition leaders in psychological as well as technical skills. Emergency drills include psychological components. Practicing response procedures reduces anxiety about potential incidents. Familiarity builds confidence even if real emergencies never occur. Environmental beauty sometimes offsets strain. Many researchers describe profound appreciation for Arctic scenery, wildlife encounters, and atmospheric phenomena such as auroras. These experiences contribute positively to overall well-being. Scientific motivation itself sustains morale. Knowing the broader importance of climate, ecological, or atmospheric research provides purpose. Purpose often strengthens endurance during challenging periods. Family support networks also matter. Pre-deployment briefings sometimes include family members, helping them understand communication patterns and logistical constraints. This shared understanding reduces stress on both sides. Funding agencies increasingly recognize psychological factors as legitimate operational considerations. Budgets include well-being resources, recreational supplies, and communication infrastructure. This institutional support reflects evolving awareness. Longitudinal studies of polar personnel continue providing insight. Data on mood variation, cognitive performance, and social dynamics inform best practices. Findings feed back into training and expedition design. Isolation effects rarely appear suddenly. They develop gradually. Early recognition of fatigue or mood changes allows intervention before problems escalate. Peer support within teams remains an important first line of response. Transition back to non-polar environments also requires adjustment. After months in controlled, isolated conditions, returning to busy urban settings can feel overwhelming. Debriefing sessions help ease that transition. Technological advances may reduce some isolation pressures in the future. Improved communication bandwidth, virtual collaboration tools, and autonomous instrumentation decrease the need for extended human presence. Still, direct observation will likely remain necessary for certain studies. Understanding psychological strain clarifies why some Arctic research projects favour shorter deployments or rotating personnel schedules. Sustained long-term presence demands not only technical capacity, but also mental resilience. These human factors sit alongside environmental, logistical, and regulatory challenges already discussed. Together they shape how scientists approach the North Pole region, deciding where extended fieldwork remains practical and where intermittent observation suffices. This balance between presence and practicality also connects with another quieter aspect of Arctic science: the existence of unexplained data gaps that researchers continue examining carefully, gaps that arise not from mystery, but from the complex interaction of environment, technology, funding, and human limits. If you spend enough time reading scientific literature about the Arctic, one pattern starts to appear quietly in the background. It is not dramatic uncertainty, and it is not a lack of knowledge overall, but rather a collection of smaller gaps in long-term data sets that researchers continue discussing carefully. These gaps do not mean scientists have no understanding of the North Pole region. They simply reflect how difficult it can be to maintain consistent measurements in an environment shaped by moving ice, extreme weather, logistical costs, regulatory constraints, equipment limitations, and human factors all at once. The result is a scientific landscape where most major trends are understood, yet certain details remain under continuous examination. Long-term climate monitoring provides a clear example. Scientists track temperature, ice thickness, ocean salinity, atmospheric chemistry, and ecological activity over decades to identify trends. Ideally, these measurements would occur continuously at fixed locations. Near the pole, maintaining that continuity proves difficult. Ice drift relocates instruments. Storms interrupt data transmission. Funding cycles pause monitoring programs temporarily. When those interruptions occur, data sets develop gaps that require careful statistical treatment. Temperature records illustrate this well. Surface air temperature near the Arctic has been monitored for many years through a combination of weather stations, drifting buoys, aircraft observations, and satellite measurements. However, station density remains lower than in most populated regions. Some areas have only intermittent measurements rather than continuous records. Scientists interpolate between available data points using models, but interpolation always carries uncertainty margins. Sea ice thickness data contains similar challenges. Satellite altimetry provides broad coverage, yet ground calibration measurements remain sparse in central Arctic regions. Ice cores drilled during expeditions offer detailed local data, but those expeditions occur seasonally rather than year-round. Researchers compare satellite estimates with occasional direct measurements to refine accuracy, though the limited calibration frequency leaves ongoing discussion about precision. Ocean circulation studies face another layer of complexity. The Arctic Ocean influences global thermohaline circulation by storing fresh water and exchanging heat with lower latitudes. Continuous deep water measurements are difficult because floats and moorings must operate beneath moving ice. Some instruments surface periodically for data transmission, but ice cover sometimes blocks surfacing. Lost instruments create data discontinuity that scientists must account for. Atmospheric chemistry monitoring encounters similar issues. Aerosol concentrations, greenhouse gas levels, and trace chemical species vary with weather patterns. Industrial emissions transported from lower latitudes, and natural processes such as sea spray. Continuous ground-based sampling stations exist but remain geographically limited. Aircraft campaigns provide snapshots rather than uninterrupted records. Biological datasets often show even larger variability. Plankton blooms, fish migration patterns, bird nesting cycles, and marine mammal behaviour depend on seasonal conditions that shift annually. Missing a sampling window due to weather or logistics can delay observations for an entire year. Long-term ecological trends therefore require patience and repeated measurement cycles. Data transmission interruptions also contribute to gaps. Satellite links sometimes experience outages due to atmospheric conditions, equipment malfunction, or bandwidth limitations. Instruments may store data locally until communication resumes. Occasionally, storage capacity fills before transmission becomes possible, leading to partial loss. Calibration differences across instruments introduce another discussion point. When new technology replaces older sensors, Overlapping measurement periods allow cross-calibration. In remote Arctic deployments, overlap periods may be short due to logistical constraints. Scientists analyze instrument performance carefully to ensure continuity, though uncertainty occasionally persists. Historical data compatibility remains an ongoing topic as well. Earlier expeditions used measurement techniques less standardized than modern methods. Digitizing old records improves long-term analysis, yet methodological differences require correction factors. Researchers debate best approaches for integrating historical observations with contemporary data sets. Satellite observation, despite its advantages, contributes its own uncertainties. Sensor drift, algorithm updates, and orbital changes affect data consistency. Continuous validation against ground measurements helps maintain reliability, but as discussed earlier, ground measurements themselves can be sparse. Short-term extreme events sometimes escape detailed documentation. Sudden ice breakup, localized storm systems, or transient ecological phenomena may occur between scheduled observations. Scientists identify these events indirectly through secondary indicators, though direct measurement would provide clearer insight. Funding variability influences data continuity too. Research programs depend on grant cycles and national budgets. When funding lapses temporarily, monitoring stations may pause operation. Restarting them later creates discontinuities that complicate trend analysis. International coordination helps reduce some gaps but introduces others. Shared data sets require harmonized measurement standards, data formats, and access policies. Establishing those standards takes time. Differences in national research priorities also influence which variables receive sustained attention. Human presence limitations intersect with data gaps as well. Extended polar deployments carry psychological and logistical constraints already discussed. Rotating personnel schedules sometimes affect observational continuity, particularly for manually collected data. Technological evolution gradually fills certain gaps while creating new transitional uncertainties. For example, autonomous underwater vehicles expand ocean monitoring capability, but require validation against traditional ship-based sampling. During transition periods, data sets combine methods with different characteristics. Statistical modelling plays an important role in addressing incomplete data. Climate models, ocean circulation simulations, and ecological forecasting tools incorporate available observations to estimate missing information. These models improve continuously, though they depend on accurate baseline data. Public communication about data gaps requires careful framing. Scientists emphasize that uncertainty does not imply ignorance. Most broad Arctic trends, including warming patterns and ice decline, remain well supported. Data gaps primarily affect finer-scale understanding rather than overall conclusions. Educational programs increasingly highlight the value of uncertainty recognition. Training researchers to communicate uncertainty clearly improves public trust and scientific collaboration. Transparency about limitations strengthens credibility. Some unexplained patterns stimulate new research questions. Unexpected temperature anomalies, irregular ice drift behavior, or unusual species distribution changes prompt targeted investigations. In this way, data gaps sometimes drive scientific innovation rather than hindering it. Emerging technologies promise gradual improvement. Expanded satellite constellations, longer endurance autonomous sensors, improved battery performance, and better communication infrastructure all reduce observation interruptions incrementally. Crowdsourced observations occasionally supplement formal data sets. Commercial shipping, tourism vessels, and local communities contribute environmental observations under structured programs. These contributions expand spatial coverage modestly. Data archiving and accessibility have improved significantly. Open access repositories allow researchers worldwide to analyze Arctic datasets collaboratively. Broader participation accelerates gap identification and solution development. Interdisciplinary research helps contextualize incomplete data. Combining atmospheric science, oceanography, ecology, and geophysics often clarifies patterns that single-discipline datasets might miss. Collaboration remains central to Arctic research progress. Climate variability itself influences data interpretation. Natural oscillations overlay long-term trends. Distinguishing between short-term variability and persistent change requires extended data sets, which reinforces the importance of continuity. Policy decisions sometimes rely on imperfect data. Environmental management, shipping regulation, and climate mitigation strategies incorporate the best available information while acknowledging uncertainty. Ongoing research aims to reduce those uncertainties over time. Scientific culture increasingly values resilience in data collection. Designing monitoring systems that tolerate interruption, self-correct, and integrate multiple observation methods improves overall reliability. Field experience contributes insight beyond raw data. Researchers' qualitative observations often guide hypothesis development even when quantitative data sets remain incomplete. Documenting those observations systematically enhances scientific value. Public interest in Arctic change continues growing. Increased awareness supports funding, collaboration, and technological development aimed at reducing data gaps. Communication plays an important role in maintaining that support. Despite remaining uncertainties, the overall understanding of Arctic environmental dynamics has advanced substantially over recent decades. Data gaps represent refinement opportunities rather than fundamental unknowns. Recognizing these gaps helps scientists prioritize future expeditions, technological investments, and collaborative initiatives. Strategic planning focuses on areas where additional data will provide the greatest benefit. These ongoing discussions about incomplete datasets connect naturally with broader environmental changes already affecting the region. Climate change, in particular, introduces new variables that reshape research priorities, sometimes creating fresh uncertainties even as older ones gradually diminish. When scientists began systematically studying the Arctic many decades ago, they were already aware that it played an important role in global climate. What has changed more recently is the pace at which environmental conditions there are shifting. Climate change is not only producing measurable effects such as warming temperatures, thinning ice, and altered ecosystems. It is also introducing new variables that researchers must account for, sometimes faster than observational systems can fully adapt. This does not mean the science is uncertain in a broad sense. The overall warming trend and ice decline remain well documented. The challenge lies in understanding the increasingly complex details emerging from those changes. One of the most visible developments is the reduction in multi-year sea ice. Historically, large portions of the Arctic Ocean remained covered by thick ice that survived several summers. That persistent ice created relatively stable conditions for certain types of research. As average temperatures rise, seasonal ice now forms later and melts earlier. The remaining ice often consists of thinner first-year ice. Thinner ice moves more easily under wind and current influence, increasing variability in drift patterns. Scientists studying ocean circulation, atmospheric exchange, and ice dynamics must adjust models continuously to account for this increased mobility. Surface reflectivity, or albedo, provides another example of a shifting variable. Ice and snow reflect a large portion of incoming solar radiation. Open water absorbs more heat. As ice coverage declines, more solar energy enters the ocean, accelerating local warming. This feedback loop has been recognized for years, yet the exact rate and spatial distribution of change vary annually. Satellite measurements help track these patterns, though ground validation remains important. Ocean stratification patterns are evolving as well. Freshwater input from melting ice, increased river discharge, and precipitation changes alter salinity gradients. These gradients influence how heat circulates through the Arctic Ocean. Subtle shifts can affect sea ice formation timing, nutrient distribution, and marine ecosystem productivity. Continuous monitoring helps clarify these relationships, though though emerging variability sometimes introduces unexpected results. Atmospheric circulation also reflects changing conditions. Temperature differences between the Arctic and lower latitudes influence jet stream behaviour. Some studies suggest that Arctic warming may contribute to altered mid-latitude weather patterns, though the exact mechanisms remain an active area of research. Establishing causal relationships requires long-term datasets, which continue to accumulate. Permafrost thaw represents another important variable. While central polar research often focuses on sea ice, surrounding Arctic land areas store large amounts of frozen organic material. As temperatures rise, thawing permafrost releases greenhouse gases such as methane and carbon dioxide. Measuring these emissions accurately requires coordinated land, air, and satellite observations. Variability in thaw rates introduces uncertainty that scientists continue to examine carefully. Ecosystem changes appear across multiple levels. Plankton blooms may occur earlier in the season due to increased light penetration through thinner ice. Fish distribution patterns adjust accordingly. Marine mammals follow prey availability shifts. Migratory birds alter timing and routes. Documenting these ecological responses requires interdisciplinary collaboration because physical environmental change cascades through biological systems. Shipping activity provides a human-related variable emerging alongside environmental change. As sea ice retreats seasonally, previously inaccessible routes become navigable for limited periods. Increased vessel traffic influences local noise levels, pollution risk, and safety considerations. Scientific monitoring expands to include these anthropogenic factors while maintaining focus on natural processes. Coastal erosion accelerates in some Arctic regions as protective sea ice declines. Waves reach shorelines more frequently, destabilizing permafrost cliffs and infrastructure. This process influences sediment transport into the ocean, which in turn affects marine ecosystems and water clarity. Monitoring coastal dynamics requires integration of land-based, aerial, and marine observations. Cloud formation patterns may shift with changing temperature gradients and moisture availability. Clouds influence both incoming solar radiation and outgoing heat. Small changes in cloud cover distribution can have significant climatic effects. Satellite observation combined with atmospheric modelling continues refining understanding of these interactions. Wildfire occurrence in some Arctic and subarctic regions has increased during warmer summers. Smoke particles transported northward affect atmospheric chemistry and ice surface reflectivity. Darker surfaces absorb more heat, contributing to localized melting. Tracking these interactions involves both remote sensing and ground measurement networks. New microbial activity in warming soils and waters represents a subtler variable. Microorganisms play roles in nutrient cycling and greenhouse gas production. Changing temperature and moisture conditions influence microbial communities. Research in this area remains ongoing, combining field sampling with laboratory analysis. Infrastructure adaptation becomes part of the scientific landscape as well. Research stations, communication systems, and transport routes originally designed for stable ice conditions require modification. These operational changes sometimes affect long-term dataset continuity. Temporal variability itself becomes a research focus. Increased year-to-year fluctuation in ice extent, temperature anomalies, and ecosystem responses complicates trend detection. Scientists refine statistical approaches to distinguish short-term variability from long-term change. Public policy interest grows alongside scientific observation. Climate negotiations, environmental protection planning, and economic development discussions increasingly reference Arctic data. Accurate communication of both known trends and remaining uncertainties supports informed decision-making. Technological innovation responds to evolving conditions. Autonomous sensors designed for thinner ice environments, improved satellite imaging techniques, and enhanced modelling tools expand observational capability. Implementation occurs gradually as testing confirms reliability. Data integration across disciplines becomes more important. Physical oceanography, atmospheric science, ecology, geology, and social science all contribute perspectives on Arctic change. Comprehensive understanding emerges from combining these viewpoints rather than treating them separately. Educational outreach reflects these developments. Universities incorporate Arctic climate studies into broader environmental science curricula. Public awareness supports sustained funding and international collaboration. Economic considerations intertwine with environmental change. Resource exploration interest, shipping opportunities, and tourism potential increase as ice conditions shift. Balancing economic activity with environmental protection requires ongoing dialogue informed by scientific evidence. Legal frameworks continue adapting. Maritime regulations, conservation zones, and indigenous rights agreements evolve in response to environmental and economic developments. Scientists often provide data supporting these policy adjustments. International cooperation remains central because Arctic processes influence global systems. Shared observation networks, joint expeditions, and data sharing agreements enhance understanding while distributing cost. Risk assessment methodologies evolve as well. Increased variability requires flexible planning for research expeditions. Safety protocols incorporate updated ice condition forecasts, weather prediction improvements, and communication infrastructure upgrades. Scientific uncertainty communication receives greater emphasis. Researchers distinguish clearly between established findings and emerging hypotheses. Transparent communication supports public trust. Long-term monitoring programs adapt to new realities by adding measurement parameters previously considered secondary. For example, increased attention to freshwater flukes, coastal sediment transport, and ecological timing reflects evolving priorities. Despite new variables, foundational physical principles remain stable. Heat exchange, atmospheric dynamics, and ocean circulation follow established laws. Climate change alters boundary conditions rather than underlying physics. Scientific patience remains essential. Many processes unfold over decades. Short-term fluctuations can obscure long-term patterns. Continued observation gradually clarifies emerging trends. Funding stability supports consistent monitoring. Interruptions complicate analysis, so agencies increasingly emphasize sustained investment in Arctic observation infrastructure. Technological redundancy reduces data loss risk. Multiple sensors, overlapping satellite coverage, and distributed observation networks improve resilience. Field experience continues informing model development. Direct observation remains valuable even as remote sensing expands. As environmental conditions evolve, so does the scientific approach. Adaptability becomes a core research skill alongside technical expertise. Understanding how climate change introduces new variables helps explain why Arctic science remains dynamic rather than settled. Progress continues, yet new questions emerge alongside answers. This evolving environmental context also connects with historical experience. Earlier expeditions encountered their own uncertainties and operational limits, some of which still inform present-day planning, especially when considering past missions that ended earlier than expected due to environmental, logistical, or technical constraints. Long before satellites, autonomous sensors and ice-strengthened research vessels became standard tools. Scientists and explorers trying to understand the far north relied on ships, sledges, celestial navigation, and a great deal of patience. Many expeditions contributed valuable knowledge, but quite a few also ended earlier than planned, not because the participants lacked skill or determination, but because Arctic conditions often proved more complex than expected. These historical experiences still influence modern research planning quietly in the background. Institutions review them not out of nostalgia, but because the practical lessons remain relevant even with improved technology. One recurring issue in early Arctic expeditions involved sea ice unpredictability. Ships designed for exploration sometimes became trapped when pack ice closed unexpectedly. Ice pressure could immobilize a vessel for months. In some cases, hulls suffered structural damage severe enough to force abandonment. Crews prepared for overwintering when necessary, though prolonged immobilization consumed supplies intended for mobile research. Even when survival was not at risk, scientific objectives shifted from exploration to endurance. Navigation challenges also contributed to premature expedition endings. Before reliable satellite navigation, explorers depended on sextants, chronometers, and magnetic compasses, all of which behaved less predictably near the pole. Cloud cover interfered with celestial sightings. Magnetic variation complicated compass use. Small navigational uncertainties accumulated over time, sometimes forcing conservative retreat decisions when fuel or food margins narrowed. Weather forecasting limitations amplified these risks. Without modern meteorological models, expeditions often encountered storms with little warning. Sudden blizzards reduced visibility, buried equipment, and delayed travel. Persistent fog made ice reconnaissance difficult. Ships sometimes remained stationary waiting for clearer conditions, again consuming supplies intended for movement. Logistical resupply represented another vulnerability. Many early expeditions depended on single-season planning. If ice conditions prevented a scheduled resupply vessel from reaching a camp or ship, options became limited. Food preservation techniques improved gradually over time, yet caloric demands in cold environments remained high. Conservative planners built contingency stores, though extended delays could still require expedition termination. Health considerations influenced outcomes as well. Nutritional deficiencies, particularly vitamin shortages, affected early polar teams before modern dietary planning became standard. Improved understanding of nutrition, along with preserved food technology, reduced such risks significantly in later expeditions. Nevertheless, medical support remained limited compared with contemporary standards. Communication constraints meant that expeditions operated largely independently once underway. Radio technology eventually improved coordination, but earlier teams had little contact with the outside world. Decision-making therefore relied entirely on local judgment. Returning early often reflected prudent risk assessment rather than failure. Equipment durability posed persistent challenges. Mechanical instruments exposed to extreme cold sometimes malfunctioned unexpectedly. Navigation tools, scientific apparatus, and even basic transport equipment such as sledges required constant maintenance. Replacement parts were rarely available once an expedition began. Ice drift also surprised early explorers. Some expeditions intentionally allowed ships to freeze into ice, hoping to drift across the Arctic Ocean while collecting data. This approach produced valuable oceanographic information, but occasionally extended far beyond initial timelines. Supplies calculated for one duration sometimes proved insufficient for the eventual drift period. Terrain obstacles along Arctic coastlines complicated land-based expeditions. Crevassed glaciers, unstable sea ice margins, and shifting snowfields slowed travel. Sledge teams adjusted routes frequently. These adjustments sometimes delayed progress enough to make seasonal return windows uncertain, prompting cautious withdrawal. Wildlife encounters, though rarely the primary cause of expedition termination, occasionally influenced operational decisions. Protecting food stores from animals and ensuring camp safety required attention that diverted effort from scientific objectives. Political factors occasionally shaped expedition timing too. International tensions, territorial claims, or administrative barriers sometimes limited access to certain regions. Researchers adjusted plans accordingly, occasionally shortening missions. Technological development gradually addressed many of these issues. Ice-strengthened hulls improved ship resilience. Radio communication enhanced coordination. Nutritional science improved expedition health. Meteorological forecasting advanced steadily. Yet even with these improvements, modern planners still review historical accounts because they illustrate how environmental variability interacts with human planning. Historical records provide baseline environmental data as well. ice extent descriptions, wildlife observations and weather logs from early expeditions contribute to long-term climate analysis. Integrating these qualitative observations with modern quantitative measurements strengthens trend interpretation. Institutional memory within polar research organizations often includes case studies of earlier expeditions. Training programs reference these examples to illustrate decision-making under uncertainty. Understanding why teams chose to turn back early helps modern researchers recognize similar risk indicators. Public perception sometimes romanticizes early Arctic exploration. While those journeys were indeed remarkable, scientists today emphasize the practical lessons more than the dramatic narratives. Risk management, preparation, and adaptability remain central themes. Archaeological work occasionally examines abandoned expedition sites. Artifacts, shelter remains, and equipment provide insight into daily life under polar conditions. Such studies combine historical scholarship with environmental science, revealing how materials degrade in cold climates. Advances in clothing technology illustrate historical progression clearly. Early explorers relied on natural fibers and fur garments. Modern synthetic insulation, moisture management fabrics, and layered clothing systems provide superior protection. These improvements reduce fatigue and injury risk during extended fieldwork. Transportation evolution also stands out. Dog sledges, once the primary means of over-ice travel, have largely been supplemented by snowmobiles, tracked vehicles, and aircraft. Each method carries advantages and limitations. Modern teams sometimes combine approaches depending on terrain and objectives. Energy supply changes reflect technological growth too. Earlier expeditions relied on solid fuels and limited portable heating options. Contemporary camps use diesel generators, hybrid renewable systems, and advanced insulation. Reliable heat supports both safety and equipment operation. Medical capability improvements significantly influence expedition planning. Portable diagnostic tools, telemedicine communication, and trained field medics enhance response capacity. Evacuation remains challenging but more feasible than in earlier periods. Scientific instrumentation itself has become more robust. Cold-resistant electronics, autonomous data loggers, and satellite-linked sensors expand research reach while reducing human exposure to extreme conditions. Historical expedition routes sometimes become modern research corridors. Established knowledge about safe passages, seasonal patterns, and logistical staging points informs current planning. Cultural exchanges with indigenous communities also developed over time. Early expeditions sometimes overlooked local expertise. Modern research increasingly incorporates indigenous knowledge, improving safety and environmental understanding. Funding structures evolved alongside institutional science. Early expeditions often relied on private sponsorship or national prestige motivations. Contemporary research typically operates within structured grant frameworks emphasizing long-term scientific value. Documentation standards improved as well. Detailed logs, standardized measurement protocols, and digital data storage enhance comparability across expeditions. Public engagement has changed too. Modern communication technology allows near real-time updates from polar research teams, increasing transparency and educational outreach. Despite these advances, early expedition lessons continue shaping modern caution. Environmental unpredictability remains. Ice still moves, weather still disrupts plans. Historical awareness reinforces respect for those realities. Understanding why some expeditions ended prematurely helps contextualize present-day research pacing. Turning back or adjusting objectives remains a sign of responsible planning rather than failure. These historical experiences blend with contemporary geopolitical considerations. As Arctic interest grows among multiple nations, scientific cooperation intersects with territorial policy, resource management, and international agreements, all of which influence how research access evolves today. When discussions about Arctic research turn toward access and long-term presence, political geography inevitably becomes part of the picture. The Arctic Ocean may look like an open expanse on a globe, but in practice it is surrounded by nations with coastlines, economic interests, security priorities, and environmental responsibilities tied to that region. Scientific research usually proceeds cooperatively, yet political considerations sometimes influence where studies happen, how data is shared, and how frequently international teams can work together in certain locations. These influences rarely stop research completely, but they can shape its pace and geographic distribution in subtle ways. Sovereignty in the Arctic is governed partly by international maritime law, particularly the United Nations Convention on the Law of the Sea. Coastal nations can claim exclusive economic zones extending from their shorelines, typically up to 200 nautical miles. Within those zones, countries regulate resource exploration, environmental protection, and research access. Scientists planning expeditions must therefore coordinate with national authorities depending on their intended study area. Permit processes are usually routine, though administrative timelines vary. Continental shelf claims represent another ongoing political discussion. Some Arctic nations have submitted evidence suggesting their continental shelves extend beyond standard economic zones. These submissions involve geological data about seabed structure. The process is technical rather than confrontational, yet it influences long-term planning for resource management and infrastructure development. Scientific seabed mapping sometimes intersects with these claims, requiring careful coordination. Shipping routes have gained attention as seasonal ice retreat opens navigation windows in parts of the Arctic Ocean. Countries bordering these routes consider safety regulation, environmental protection, and economic opportunity simultaneously. Research vessels often share the same waterways as commercial shipping during ice-free periods. Coordinating navigation safety measures benefits both sectors but adds administrative complexity. Resource exploration interest contributes another dimension. Hydrocarbon deposits, mineral resources, and fisheries attract economic attention. Governments balance development potential with environmental protection. Scientific data informs these decisions, which makes research politically relevant even when conducted purely for academic purposes. Military presence in the Arctic tends to focus on monitoring and infrastructure rather than active confrontation. Radar installations, airfields, and maritime patrol capabilities support national security and search and rescue readiness. Scientific expeditions occasionally coordinate with defense agencies for logistical support such as air transport or emergency response planning. Cooperation often outweighs tension in practical terms. Diplomatic cooperation has historically characterized Arctic science. International research stations, shared icebreaker missions, and collaborative satellite programs demonstrate this pattern. Scientific diplomacy often continues even when broader political relations fluctuate. Researchers frequently maintain professional relationships across national boundaries. Data sharing agreements help maintain transparency. Many climate and environmental datasets are openly available regardless of national origin. Shared understanding of Arctic change benefits all countries because global climate systems are interconnected. Maintaining open data policies supports collective decision-making. Indigenous governance plays an increasingly visible role in Arctic sovereignty discussions. Indigenous communities possess cultural, economic, and environmental ties to northern regions. Their participation in policy decisions influences research access, environmental protection measures, and infrastructure development. Collaborative research projects often involve Indigenous organisations directly. Environmental protection agreements sometimes transcend national boundaries. Migratory wildlife, ocean currents, and atmospheric systems do not follow political borders. Cooperative conservation strategies therefore require multinational coordination. Scientific research supports these agreements by providing shared evidence. Infrastructure investment patterns reflect political priorities as well. Icebreaker fleets, research stations, satellite ground facilities, and communication networks represent long-term commitments. Countries with stronger Arctic infrastructure maintain more continuous scientific presence. Collaborative use of these facilities helps distribute access more evenly. Economic development considerations include tourism growth, shipping services, and energy exploration. Each sector interacts with scientific research differently. Tourism increases logistical demand but can also provide transportation infrastructure. Energy exploration may fund environmental studies while raising regulatory scrutiny. Legal frameworks evolve gradually. Maritime boundary agreements, environmental regulations, and resource management policies adapt to changing conditions. Scientists monitor these developments because regulatory clarity influences research feasibility. Media narratives sometimes emphasize geopolitical competition more strongly than day-to-day scientific cooperation would suggest. Researchers working in the Arctic often describe a pragmatic, collaborative atmosphere focused on shared environmental understanding. Climate change has intensified international attention on the region. Melting ice affects shipping, ecosystems, and resource accessibility. Governments therefore invest more in monitoring and forecasting. Scientific research benefits from this increased interest, though coordination remains essential. Emergency response collaboration illustrates practical cooperation clearly. Search and rescue agreements among Arctic nations ensure assistance regardless of nationality. Scientific expeditions rely on these frameworks for safety planning. Funding mechanisms sometimes reflect political priorities. National research budgets emphasize areas aligned with strategic interests. This alignment can influence which Arctic subregions receive sustained observation. Educational exchanges contribute to long-term cooperation. Student programs, joint training exercises, and collaborative academic conferences foster professional relationships across borders. These networks support ongoing research partnerships. Communication infrastructure development often involves international coordination. Satellite networks, fiber optic cables, and data relay stations serve multiple countries. Scientific data transmission benefits from these shared systems. Regulatory transparency has improved over time. Online permit systems, standardized documentation requirements, and clearer communication channels reduce administrative uncertainty for researchers. Scientific advisory roles within governments highlight the intersection of research and policy. Experts contribute environmental assessments informing navigation safety, conservation planning, and infrastructure development. Economic fluctuations influence political attention to the Arctic. Commodity prices, shipping demand, and energy markets affect national investment levels. Research funding sometimes follows these broader trends. Public awareness campaigns increasingly emphasize Arctic environmental importance. Climate education, documentary media, and outreach initiatives shape public support for continued research. Technological independence efforts occasionally intersect with sovereignty discussions. Countries invest in domestic satellite systems, research vessels, and data processing capabilities. These investments enhance national research capacity while complementing international collaboration. Cultural diplomacy also plays a role. Scientific cooperation often continues even when political relations experience tension elsewhere. Shared environmental concern provides common ground. Institutional memory within research organizations helps navigate political variability. Established partnerships, legal expertise, and experienced administrative staff streamline permit processes and collaboration agreements. Environmental monitoring requirements associated with commercial development sometimes expand scientific observation networks. Industry-funded monitoring programs contribute data alongside academic research. Policy discussions increasingly incorporate long-term climate risk assessment. Arctic changes influence global weather, sea level, and ecosystems. Scientific evidence supports international climate policy development. Risk communication remains important. Scientists present findings objectively, avoiding politicization while acknowledging policy relevance. Maintaining credibility supports constructive dialogue. International research funding programs encourage cross-border collaboration explicitly. These programs help sustain scientific networks independent of short-term political fluctuations. Standardization of measurement protocols facilitates data sharing across national programs. Harmonized methodologies improve comparability and reduce duplication. Scientific publications often include multinational authorship reflecting collaborative fieldwork. Peer review processes reinforce methodological rigor regardless of national origin. Technology transfer agreements sometimes accompany joint research initiatives. Shared innovation benefits multiple countries while advancing scientific capability. Public interest in Arctic sovereignty issues fluctuates, often influenced by media coverage of shipping routes or resource exploration. Scientific communication helps provide context. Overall, political factors shape Arctic research conditions but rarely halt scientific progress entirely. Cooperation remains the dominant operational mode, supported by shared environmental concern and mutual practical benefit. These geopolitical considerations fit alongside technological advancement trends. As new observation tools, autonomous systems, and improved infrastructure expand access gradually, scientific work continues adapting to both environmental realities and administrative frameworks, which naturally leads toward considering how modern technology is steadily improving research capability in the Arctic despite persistent challenges. If you look at Arctic research from a long historical perspective, one trend becomes clear without much effort. Access has gradually improved, not suddenly, not dramatically all at once, but step by step as technology evolves. The North Pole region still presents challenges, yet modern tools have reduced some of the barriers that once limited how often scientists could observe, measure, and document environmental conditions there. This expansion of access does not eliminate risk or cost, but it steadily changes what kinds of research become practical. Satellite technology remains one of the most influential developments. Earlier generations of polar researchers depended almost entirely on physical presence. Today, high-resolution imaging satellites, radar altimetry systems, atmospheric sounding instruments, and ocean color sensors provide continuous large-scale observation. These platforms monitor sea ice extent, temperature patterns, atmospheric circulation, and ecosystem indicators across vast areas. Although ground validation remains essential, satellites extend observation reach far beyond what field teams alone could manage. Communication systems have improved alongside observation capability. High-latitude satellite networks, though still developing, allow more reliable voice, data, and video links between Arctic expeditions and research centres. This connectivity supports real-time troubleshooting, collaborative analysis, and remote mentoring. Researchers no longer operate in complete informational isolation the way earlier expeditions sometimes did. Autonomous instrumentation has expanded dramatically as well. Drifting buoys equipped with sensors track ice movement, atmospheric conditions, and ocean properties continuously. Underwater gliders travel beneath ice, collecting salinity, temperature, and current data. Surface drones survey ice morphology and weather patterns without requiring constant human supervision. These platforms reduce the need for large permanent camps while increasing temporal coverage. Battery technology improvements support these autonomous systems. Higher energy density, better cold weather chemistry, and improved insulation techniques extend operational duration. Instruments that once functioned for weeks now operate for months or longer under similar conditions. Engineers continue refining these systems because reliability remains critical. Material science advances contribute quietly but significantly. Cold-resistant composites, improved insulation foams, corrosion-resistant metals, and flexible cold-rated polymers enhance equipment durability. These materials reduce failure rates and maintenance frequency, which lowers logistical demand over time. Navigation technology has progressed substantially too. Differential GPS, inertial navigation systems, and integrated mapping software allow precise positioning even near the pole, where traditional compass navigation becomes unreliable. This accuracy supports safe transport, consistent instrument placement, and reliable data interpretation. Icebreaker ship design has evolved. Modern research icebreakers combine reinforced hull structures, powerful propulsion systems, advanced radar imaging, and onboard laboratories. They can operate longer in heavy ice conditions than earlier vessels. Some include helicopter decks and autonomous vehicle launch capability, extending observational reach further. Aircraft technology has also adapted. Cargo planes capable of ice runway operations, long-range helicopters, and unmanned aerial vehicles all support Arctic research. Drones, in particular, provide flexible short-range observation without exposing personnel to hazardous terrain. Remote sensing instruments have diversified. Synthetic aperture radar penetrates cloud cover and darkness, allowing continuous ice monitoring. LIDAR systems measure surface elevation precisely. Microwave radiometers estimate sea ice concentration and atmospheric moisture. Combining multiple sensing modalities improves data reliability. Data processing capability has expanded alongside data collection. High-performance computing allows scientists to analyze massive data sets rapidly. Climate models incorporate finer spatial resolution. Machine learning tools assist pattern detection in complex environmental data. These computational advances help extract more insight from available observations. Telemedicine technology supports personnel safety. Portable diagnostic equipment and secure communication links allow remote medical consultation. Field teams receive expert guidance quickly, improving response to health concerns. Energy systems show gradual innovation as well. Hybrid power setups combining diesel generators with wind turbines, solar panels, and advanced battery storage reduce fuel consumption. While renewable energy use in polar regions remains technically challenging, incremental progress continues. Autonomous underwater vehicles deserve special mention. These robotic platforms operate beneath ice cover where ships cannot easily reach. They map seafloor topography, measure ocean chemistry, and monitor biological activity. Advances in navigation algorithms, battery endurance, and sensor integration steadily improve their reliability. Environmental monitoring networks increasingly use distributed sensor arrays. Multiple small instruments provide redundancy and broader spatial coverage compared with single large installations. Network resilience improves because failure of one unit does not compromise entire datasets. Portable laboratories have become more capable. Compact analytical equipment allows preliminary sample processing directly in the field. This capability reduces sample degradation risk and accelerates research cycles. Logistics planning benefits from digital simulation tools. Ice movement models, weather forecasting improvements, and route optimization software help planners choose safer deployment windows. These predictive tools reduce uncertainty, though they never eliminate it entirely. Education and training technology contributes indirectly. Virtual reality simulations prepare researchers for polar conditions before deployment. Online collaboration platforms connect international teams effectively. Shared digital resources support knowledge transfer across institutions. Public engagement technology also plays a role. Leave expedition updates, educational streaming, and open access data portals increase transparency. Greater public awareness often translates into sustained research funding support. Miniaturization trends continue across instrumentation. Smaller sensors require less power, reduce transport weight, and allow deployment in greater numbers. This shift enhances spatial coverage without proportional cost increases. Rescue and safety technology has improved. Personal locator beacons, advanced weather forecasting, improved survival gear, and reliable communication devices enhance expedition safety margins. These tools support longer deployments with reduced risk. Data archiving infrastructure ensures long-term accessibility. Cloud storage, standardized metadata protocols, and collaborative databases preserve information for future analysis. Historical continuity strengthens climate research reliability. Regulatory compliance technology helps streamline administrative processes. Digital permit systems, environmental impact tracking tools, and automated reporting platforms reduce paperwork burden, allowing scientists to focus more on research. International collaboration platforms support shared mission planning. Joint expeditions benefit from coordinated logistics, pooled funding, and standardized methodologies. Technology facilitates this cooperation efficiently. Artificial intelligence assists predictive maintenance for equipment. Sensors monitor performance indicators and alert teams before failures occur. Preventive maintenance reduces unexpected downtime. Climate monitoring specifically benefits from integrated observation networks. Satellite data, autonomous sensors, ship observations, and atmospheric measurements combine into comprehensive data sets. Integration enhances understanding of complex Arctic systems. Transportation efficiency improvements gradually lower operational cost. More efficient engines, better fuel management systems, and optimized route planning reduce expenditure over time, though Arctic logistics remain expensive overall. Environmental impact monitoring technology ensures compliance with protection regulations. Sensors detect potential contamination early, supporting responsible research practices. Scientific culture adapts alongside technology. Researchers increasingly design projects assuming hybrid observation methods combining fieldwork and remote sensing. Flexibility becomes standard practice. Despite progress, limitations remain. Technology expands access slowly rather than eliminating challenges outright. Ice still moves, weather still disrupts plans, and environmental protection requirements remain essential. The trend, however, points toward increasing capability year by year. You can see this gradual expansion reflected in the growing number of datasets available, the diversity of research disciplines active in the Arctic, and the increased frequency of international collaboration. Each technological step adds a little more stability to what was once an extremely uncertain operational environment. These advances also shape future expectations. Scientists increasingly focus not only on overcoming access barriers, but on identifying what new knowledge those improved tools can provide. That naturally leads into considering what researchers hope to learn next, as observation capability continues expanding across the far northern regions. If you ask researchers working in Arctic science what still motivates them to return year after year despite the logistical effort, the answer rarely centres on adventure or novelty. Most speak about unanswered questions that have become more precise over time. Earlier expeditions often aimed simply to observe and map. Today, the focus has shifted toward understanding processes in detail, identifying feedback loops, and improving predictive capability. The Arctic is no longer viewed only as a remote region to explore. It is increasingly understood as a dynamic component of the global environmental system, and that recognition shapes what scientists hope to learn next. Climate dynamics remain at the top of the list. Scientists want clearer understanding of how Arctic warming interacts with global weather systems. Temperature gradients between polar and mid-latitude regions influence atmospheric circulation patterns. Some research suggests links between Arctic warming and certain weather anomalies further south, though the mechanisms remain under investigation. Refining these relationships requires long-term atmospheric measurements, improved climate models, and integrated datasets combining ocean, ice, and air observations. Sea ice behaviour continues to attract attention beyond simple extent measurement. Researchers now examine structural properties of ice, melt pond formation, salinity gradients within ice layers, and mechanical strength variations. These details affect how quickly ice forms or melts, and how it interacts with ocean currents and atmospheric heat exchange. Understanding these finer scale processes improves forecasting accuracy. Ocean circulation beneath the Arctic ice cap represents another priority. The Arctic Ocean stores fresh water from melting ice and river inflow. Changes in freshwater distribution influence global ocean circulation, including thermohaline currents that affect climate worldwide. Scientists hope to clarify how warming trends alter these circulation patterns over decades. Biological ecosystem responses form a major research frontier as well. Earlier ecological studies focused on species presence and seasonal patterns. Current research looks more closely at food web interactions, genetic adaptation to changing temperatures, and migration timing shifts. Plankton blooms, fish distribution, marine mammal feeding behaviour, and bird nesting cycles all reflect environmental change in complex ways. Microbial ecology has gained increasing interest. Microorganisms in Arctic soils, ice, and ocean water play important roles in carbon cycling. As temperatures rise, microbial activity may accelerate greenhouse gas release. Measuring these processes accurately helps improve climate projections. Advances in molecular biology allow detailed analysis that was not possible in earlier decades. Permafrost monitoring extends beyond land-based studies into coastal interactions. Scientists investigate how thawing permafrost contributes sediment, nutrients, and greenhouse gases to the Arctic Ocean. This land-ocean linkage represents an emerging research area with implications for both ecosystems and climate modelling. Atmospheric chemistry research continues evolving. Arctic air masses carry pollutants transported from lower latitudes. Measuring aerosol composition, ozone levels, and trace gases helps scientists understand long-range environmental interactions. These studies inform both climate science and environmental policy. Acoustic monitoring of Arctic marine environments is expanding. Sound propagation changes as ice cover varies. Scientists study how these acoustic shifts affect marine mammals and human activities such as shipping. Improved acoustic data sets support both ecological understanding and navigation safety. Geological research beneath Arctic waters seeks better mapping of seafloor structures. Bathymetry influences ocean circulation, sediment transport, and ecosystem distribution. Advances in sonar mapping technology allow more detailed surveys even under ice cover. Hydrological studies examine freshwater input from rivers flowing into the Arctic Ocean. Seasonal discharge patterns, sediment load changes, and temperature variation all influence coastal ecosystems. Integrated monitoring programs combine river data with marine observations. Weather forecasting improvement remains a practical goal. Arctic atmospheric conditions influence global weather patterns. Better polar observation enhances forecast accuracy beyond the region itself. Meteorological agencies collaborate closely with scientific institutions on this front. Human activity monitoring has become more prominent. Increased shipping, tourism, and resource exploration introduce environmental variables that require study. Scientists track pollution levels, noise impact, and ecosystem response to human presence. Indigenous knowledge integration represents an expanding research dimension. Traditional ecological observations provide valuable long-term perspective on environmental change. Collaborative projects combine scientific instrumentation with local expertise, improving data richness. Technological experimentation itself becomes a research focus. New sensor designs, autonomous platforms, and communication systems undergo field testing in Arctic conditions. Successful technologies often later support research in other extreme environments. Carbon cycle studies in the Arctic attract global attention. Scientists aim to quantify how much carbon is stored in ice, ocean water, and permafrost, and how quickly it may be released under warming scenarios. These measurements influence climate mitigation strategies. Sea level research connects Arctic observations with global coastal planning. Ice melt contributions to ocean volume require precise measurement. Satellite altimetry combined with field data improves accuracy. Glaciology research extends to Greenland's ice sheet interactions with the Arctic Ocean. Meltwater discharge patterns influence ocean salinity and circulation. Long-term monitoring helps clarify these relationships. Energy balance studies examine how solar radiation, atmospheric conditions, and surface reflectivity interact. These processes determine local warming rates. Improved understanding enhances climate model performance. Wildlife conservation research continues alongside environmental monitoring. Population health assessments, habitat usage studies, and migration tracking inform conservation policy decisions. Educational outreach goals increasingly accompany scientific objectives. Researchers aim not only to collect data, but also to communicate findings clearly to the public. Transparency supports informed discussion about environmental change. Interdisciplinary collaboration remains central. Arctic science rarely fits within a single academic field. Oceanographers, atmospheric scientists, ecologists, geologists, engineers, and social scientists often work together. Data integration challenges drive methodological innovation. Combining satellite data, field measurements, historical records, and modelling outputs requires advanced analytical tools. Artificial intelligence assists pattern detection and prediction. Long-term observation infrastructure expansion remains a priority. Permanent or semi-permanent monitoring networks provide continuity essential for detecting subtle trends. Risk assessment research supports safe Arctic operations. Understanding ice dynamics, weather variability, and ecological sensitivity helps guide both scientific expeditions and commercial activity. Policy-relevant science receives growing attention. Environmental management decisions increasingly rely on robust Arctic data. Researchers strive to provide clear, objective evidence for policymakers. Public interest encourages continued funding. Climate awareness, educational media, and scientific communication efforts maintain attention on Arctic research importance. Technological miniaturization allows broader sensor deployment. Distributed networks improve spatial coverage without proportional cost increase. Open data initiatives facilitate global collaboration. Shared data sets accelerate discovery and improve reproducibility. Historical data re-evaluation remains ongoing. Digitizing expedition logs and integrating them with modern datasets enhances long-term perspective. Scientific curiosity persists, even as understanding improves. Each answered question often reveals additional complexities rather than final closure. Operational experience informs future research design. Lessons learned from past expeditions improve efficiency and safety. Funding stability supports continuity. Institutions advocate sustained investment recognizing long-term global benefits. Ethical considerations guide research expansion. Environmental protection and community engagement remain central principles. Climate adaptation research links Arctic findings to global resilience planning. Insights gained there inform broader environmental strategies. Ultimately, scientists hope not only to gather more data, but to build a clearer, integrated understanding of how the Arctic functions within the Earth system. That understanding develops gradually through consistent observation, technological innovation, and international cooperation. As those efforts continue, attention naturally shifts toward broader reflection on what the Arctic represents scientifically today, not as an unreachable frontier, but as one of the remaining environments where careful, patient study still steadily reveals new insight about the planet as a whole. By the time most people finish hearing about Arctic research, a quiet shift usually happens in how the North Pole is imagined. It stops being just a white circle at the top of a map or a distant symbol of cold and isolation. Instead, it starts to look more like a working scientific environment. Complex, carefully studied, but still carrying elements that resist easy observation. That combination explains why researchers continue returning. Not because it is completely unknown, and not because it is inaccessible in a dramatic sense, but because it remains one of the few regions where environmental processes unfold in ways that still require steady, patient investigation. The idea of a scientific frontier today does not mean the same thing it did centuries ago. Earlier exploration focused on geographic discovery, mapping coastlines, identifying routes, establishing presence. Modern science approaches frontiers differently. The emphasis now lies on understanding systems, measuring change over time, and integrating observations into global knowledge networks. The Arctic fits that definition well. It influences weather, ocean circulation, ecological balance, and climate stability far beyond its geographic boundaries. Researchers often describe the Arctic as both fragile and resilient. Fragile because ecosystems there respond slowly to disturbance and recover gradually. Resilient because species and environmental processes have adapted to extreme conditions over long evolutionary periods. Studying that balance helps scientists understand how environmental systems respond to stress, which has implications well beyond polar regions. Long-term climate monitoring continues to anchor much of the scientific interest. Temperature trends, ice thickness variation, ocean heat content, and atmospheric chemistry all provide insight into global climate dynamics. These measurements are rarely dramatic on a day-to-day basis. Instead, they accumulate slowly, forming data sets that become increasingly valuable over decades. The patient accumulation defines much of modern Arctic science. The region also offers opportunities to study fundamental physical processes, heat exchange between ocean and atmosphere, cloud formation under unique temperature gradients, sea ice mechanical behaviour, and freshwater circulation all provide natural laboratories for Earth system science. Observations made there refine models used worldwide. Ecological research contributes another important perspective. Arctic species often occupy specialised niches shaped by seasonal light cycles, temperature extremes, and ice availability. Changes in these conditions reveal how ecosystems adapt to environmental stress. Insights gained inform broader biodiversity conservation strategies. Technological innovation frequently finds testing ground in polar conditions. Instruments designed to withstand extreme cold, autonomous monitoring systems, advanced communication technologies, and energy-efficient infrastructure often mature through Arctic deployment before broader application. This technological feedback loop benefits scientific capability globally. International cooperation remains one of the most distinctive aspects of Arctic research. Scientists from multiple countries routinely collaborate on expeditions, data analysis, and modelling efforts. Shared environmental interest tends to encourage practical cooperation, even when political contexts fluctuate elsewhere. That collaborative culture helps maintain continuity and observation. Public understanding of the Arctic has grown noticeably. Educational outreach, documentaries, and accessible scientific communication make the region less abstract to wider audiences. Increased awareness often translates into sustained research funding and support for environmental protection policies. Economic interest continues to intersect with scientific priorities. Shipping routes, tourism activity, resource exploration, and infrastructure development all influence research logistics. Scientists provide data that helps guide responsible decision-making in these areas. Indigenous communities remain essential partners in Arctic research. Traditional ecological knowledge complements scientific measurement. Long-term local observation provides context that short-term expeditions cannot replicate. Collaborative projects increasingly reflect this mutual respect. Environmental protection frameworks aim to preserve ecological integrity while allowing responsible research. Regulations shape how studies are conducted, not whether they occur. Scientists generally view these frameworks as necessary safeguards rather than obstacles. Technological progress gradually reduces operational difficulty. Better navigation tools, improved satellite coverage, autonomous instruments, and efficient energy systems expand research capability incrementally. Access improves, though environmental realities still set limits. Funding stability continues to influence research continuity. Long-term observation requires sustained investment. institutions increasingly recognize the global importance of Arctic data, supporting ongoing monitoring programs. Psychological and logistical factors remain part of planning. Research teams balance operational efficiency with well-being considerations. Rotational deployment strategies improve communication, and supportive infrastructure help maintain resilience. Historical experience informs present-day caution. Early expeditions taught practical lessons about preparation, flexibility, and environmental respect. Those lessons remain relevant even with modern technology. Scientific uncertainty persists in specific areas, not because of ignorance, but because environmental systems are inherently complex. Recognizing uncertainty strengthens research design rather than undermining confidence. Data integration across disciplines continues improving. Combining atmospheric science, oceanography, ecology, geology, and social science provides more comprehensive understanding. Interdisciplinary collaboration defines much of current Arctic research. Climate change keeps the region scientifically active. Environmental conditions evolve, introducing new questions even as others become clearer. Adaptive research strategies help maintain relevance. Policy engagement increasingly relies on Arctic data. Environmental management, climate mitigation, and economic planning benefit from accurate observation. Scientists contribute evidence while maintaining objectivity. Education and training programs prepare future researchers with both technical and interdisciplinary skills. Continued expertise development supports sustained observation capacity. Autonomous systems expand observational reach, though human presence remains essential for certain measurements. Hybrid approaches combining remote sensing and fieldwork characterize modern methodology. Data transparency strengthens public trust. Open access data sets allow broader participation in analysis and foster collaborative discovery. Risk management remains integral. Safety planning incorporates environmental unpredictability, equipment reliability, and human factors. Technological miniaturization continues enabling distributed sensor networks. Greater spatial coverage improves environmental monitoring precision. Cultural appreciation of polar environments grows alongside scientific interest. Photography, art, and storytelling contribute to public engagement without overshadowing scientific priorities. Environmental ethics guide research conduct. Minimizing disturbance ensures that observation does not compromise the systems being studied. Scientific patience defines the overall pace. Major insights often emerge from long-term data sets rather than short-term expeditions. Operational experience accumulates gradually. Each field season contributes lessons that improve subsequent planning. International scientific diplomacy continues fostering cooperation. Shared environmental challenges encourage collaborative approaches. Public curiosity remains a powerful driver. Interest in climate, ecosystems, and exploration supports sustained research investment. Technological resilience improves year by year, reducing failure rates and enhancing safety. Environmental monitoring networks expand slowly but steadily, improving data continuity. Policy frameworks evolve in response to new scientific findings, reinforcing adaptive management. Ultimately, the Arctic remains a region where careful observation still yields meaningful discovery, not dramatic revelation, not hidden secrets waiting suddenly to emerge, but steady accumulation of understanding about how a critical part of the Earth system operates. And as research continues, attention stays focused not on reaching a final endpoint, but on maintaining that ongoing observation, because the far north continues changing, continues influencing global systems, and continues offering scientists a place where patience, cooperation, and careful measurement still make a lasting difference.